Welcome to our deep dive into one of the most intriguing aspects of modern cosmology, the cosmic microwave background, or CMB. This faint glow, almost imperceptible, blankets the cosmos and holds the secrets of the universe's beginnings. Today, we embark on a journey that spans from the theoretical predictions of the early 20th century to groundbreaking discoveries and beyond. Our exploration will uncover how the CMB was predicted, discovered, and meticulously studied through advanced space missions. The CMB is not just a relic of the past. It is a cornerstone of cosmological evidence that supports the Big Bang theory. It offers us a snapshot of the universe when it was only 380,000 years old, far younger than its current age of approximately 13.8 billion years. Throughout this video, we'll meet the key figures whose work has been pivotal in unlocking the mysteries carried by these ancient photons. Their stories are not only about scientific discovery but also about unexpected surprises and the relentless pursuit of knowledge. We'll delve into the technical details of how the CMB is studied, from the construction of sensitive instruments to the interpretation of complex data that these tools provide. This includes looking at the entire spectrum of radiation and understanding the minute fluctuations that carry profound cosmological implications. Our narrative will also cover the significant missions that have shaped our current understanding of the CMB, such as COBE, WMAP, and Planck. Each of these missions has contributed unique pieces to the cosmic puzzle, refining our picture of the universe's early moments. The implications of CMB observations are vast. They extend beyond the realms of theoretical physics and into the domains of philosophy and existential inquiry. What does the CMB tell us about the origin and fate of the universe? How does it challenge our perceptions of time and space? Moreover, the story of the CMB is far from complete. As technology advances, new missions are being planned that promise to probe the CMB with even greater precision. These future projects aim to answer questions that we are only beginning to ask. In discussing the future, we will speculate on what mysteries of the universe the next generation experiments might unveil. This is an exciting time in cosmology, as new theories and models are proposed to explain the data collected from observations of the CMB. In closing, we reflect on the profound impact that studying the CMB has had on our understanding of the cosmos. It has reshaped fundamental concepts and introduced new questions in the quest to understand the cosmos. By the end of this video, you will have a clearer picture of why the cosmic microwave background is considered one of the most important observations in the field of astronomy and cosmology. It's a testament to human curiosity and the relentless pursuit of understanding our universe. Stay with us as we explore the fascinating story of light from the dawn of time, shedding light on how the universe has evolved and continues to surprise us with its complexity and wonder. As we go through each segment, we invite you to ponder the vastness of the universe and the small yet significant place we occupy within it. This is not just a story about the cosmos, it's also a story about us, about our quest to reach beyond our limits and understand the fundamental truths of nature. Thank you for joining us on this extraordinary journey. Let's begin our exploration of the cosmic microwave background and discover together the echoes of the Big Bang. The cosmic microwave background, or CMB, is essentially the afterglow of the Big Bang, the universe's explosive birth. It is composed of radiation that fills the entire universe and serves as a snapshot of the cosmos at a very early stage, long before stars and galaxies formed. Think of the CMB as the oldest light we can observe, dating back to when the universe was just 380,000 years old. At this time, the universe had cooled sufficiently for photons to travel freely, creating a uniform glow that permeates all of space. This background radiation is remarkably uniform in all directions, but it contains tiny temperature fluctuations. These fluctuations are critical as they represent the seeds from which all the structure in the universe grew: galaxies, clusters of galaxies, and vast cosmic voids. The CMB is detected as a faint signal, almost perfectly isotropic, that is not associated with any star, galaxy, or other celestial body. This is why it provides a unique, pristine view of the early universe, free from the complexities of later cosmic structures. Measured at a temperature of just 2.7 degrees above absolute zero, the CMB is a relic of the time when the universe transitioned from being opaque to transparent. The drop in temperature is a result of the universe's expansion over billions of years. In terms of spectrum, the CMB is a perfect example of a black-body radiation, fitting the theoretical predictions almost exactly. This remarkable consistency with theoretical models provides one of the strongest lines of evidence in support of the Big Bang theory. The discovery of the CMB in the mid-20th century was a monumental milestone in cosmology. It shifted the scientific consensus toward the Big Bang theory and away from competing models such as the steady-state theory. The uniformity of the CMB is one of its most astounding features, suggesting that the early universe was incredibly homogeneous. Yet, the small variations in temperature are what allow cosmologists to learn about the distribution of matter and energy in the early cosmos. Studying the CMB also gives us insights into the fundamental forces at play in the early universe. Through this exploration, we gain understanding about the nature of dark matter and dark energy, two of the most mysterious aspects of the cosmos. Each photon of the CMB has traveled through space for over 13 billion years, barely interacting with matter. This journey makes the CMB an unparalleled tool for peering back into the early universe, offering clues that are not accessible through any other means. The CMB is essentially a cosmic background noise that permeates the entire universe. Detecting and analyzing this noise requires sophisticated technology and methods, highlighting the incredible ingenuity of astronomers and physicists. Through detailed measurements of the CMB, scientists can reconstruct the conditions of the early universe with remarkable accuracy. This enables a better understanding of how the universe has evolved from its initial simplicity to its current complexity. The analysis of the CMB has also led to precision cosmology, where the parameters describing the universe, such as its age, rate of expansion, and composition, are measured with unprecedented accuracy. The CMB's importance cannot be overstated. It serves as a cornerstone of our current understanding of the universe's history and structure, confirming many aspects of the Big Bang model and challenging scientists to rethink others. As we continue to study the CMB with ever more sophisticated instruments, our understanding of the cosmos continues to evolve. This journey of discovery is far from over, with each new finding prompting more questions and leading to greater insights into the fabric of the universe. The importance of the cosmic microwave background in understanding the universe cannot be overstated. It is the linchpin in our comprehension of the universe's origin, structure, and ultimate fate. This ancient light provides us with a direct image of the universe at its infancy, offering a baseline from which we can measure all subsequent cosmic evolution. By analyzing the CMB, scientists can confirm key predictions of the Big Bang theory. This includes the universe's rate of expansion, the presence and distribution of dark matter, and the existence of dark energy. Each of these components plays a crucial role in shaping the cosmos as we see it today. The CMB also helps us to test the principles of general relativity in a cosmological context. Einstein's theory predicts how the gravity of all matter and energy affects the universe's expansion, and the CMB data align beautifully with these predictions, reinforcing the theory's cosmological applications. Moreover, the CMB provides the earliest possible snapshot of the universe's matter distribution. By studying the slight temperature variations in the CMB, cosmologists can trace the seeds of cosmic structures, learning how galaxies and clusters of galaxies formed and evolved. Through precise measurements of the CMB's temperature fluctuations, cosmologists can also determine the geometry of the universe. This research has led to the surprising discovery that the universe is flat, which has profound implications for our understanding of cosmic history and its future. The study of the CMB even touches on the mysterious epoch of cosmic inflation, an extremely brief period when the universe expanded exponentially. The characteristics of the CMB support the idea that inflation smoothed out any initial irregularities in energy and matter distribution right after the Big Bang. Another crucial aspect of CMB research is its role in fine-tuning the standard model of particle physics. The conditions of the early universe, as revealed through the CMB, provide a testing ground for theories about fundamental particles and forces, many of which are unreachable in terrestrial laboratories. The CMB also acts as a backdrop against which we measure other cosmic phenomena. For instance, by observing how galaxies move relative to the CMB, astronomers can study how gravity acts over vast distances, providing insight into the behavior of dark energy. Furthermore, the CMB is essential for cosmology's numerical models. With CMB data, cosmologists refine simulations of the universe's growth from its earliest stages to the present day, testing theories about the formation and evolution of cosmic structure. In terms of scale, the CMB allows us to place Earth in a broader cosmic context. It shows that the laws of physics hold across the vast expanse of the universe, reinforcing the idea that Earth is not in a unique or central position. The ongoing study of the CMB is pushing the boundaries of technology and computation. Each generation of telescopes and instruments designed to measure the CMB more accurately provides not only more data, but also stimulates technological advancements that have broader applications. By continuing to explore the CMB, we hope to answer some of the most fundamental questions about the universe. For instance, why is the universe made more of matter than antimatter? The clues to this asymmetry may lie in the detailed analysis of the CMB. The CMB's uniformity also poses a significant question about the connectivity of the universe. Why is it so isotropic when different regions should not have been able to equalize their temperatures due to the limits imposed by the speed of light? The answer lies in understanding the very fabric of space-time. In future missions aiming to probe the CMB with even greater detail, we expect to uncover nuances in the polarization of this ancient light. Such studies could reveal more about the universe's first moments and the properties of gravity on cosmic scales. In summary, the cosmic microwave background is not just an echo of the Big Bang, but a beacon that illuminates our understanding of the entire cosmos. It connects the realms of quantum mechanics, relativity, and thermodynamics into a cohesive narrative of the universe's history. As we peel back layers of the cosmic microwave background, we inch closer to answering the ultimate questions of our existence and the nature of reality itself. Long before the discovery of the cosmic microwave background, cosmologists and astronomers speculated about the origins of the universe. The early 20th century witnessed the birth of several significant theories that attempted to describe the universe from its inception. One such theory was the Big Bang theory, which proposed that the universe began as a singular, infinitely dense point. According to this model, the universe has been expanding ever since this initial explosion, a concept supported by the observed redshift of distant galaxies. Another competing theory was the steady-state theory, which argued that the universe has always looked the same as it does now and will continue to do so forever. This theory suggested that new matter is continuously created as the universe expands, maintaining a constant density. The concept of an expanding universe was first proposed by Alexander Friedmann in the 1920s, based on his solutions to Einstein's equations of general relativity. Friedmann's models introduced the idea that the universe could be expanding, contracting, or static, depending on its total energy density. Georges Lemaitre, a Belgian priest and physicist, independently arrived at a similar conclusion and proposed that the universe began with a primeval atom, or what he described as a cosmic egg, exploding at the moment of the creation, which led to the expansion of the universe. Einstein himself was initially skeptical of the idea of an expanding universe, favoring a static model. However, he later called his failure to predict the universe's expansion as the biggest blunder of his life, after Hubble's observation of the expanding universe in 1929. Hubble's discovery of the expanding universe provided the first observational support for these theoretical models. By measuring the redshifts in the light from distant galaxies, Hubble showed that galaxies are moving away from us in all directions, implying that the universe itself is expanding. This expansion led to the understanding that the universe must have been hotter and denser in the past. This realization opened the door to the idea that the early universe was a very different place from what we see today. Gamow, Alpha, and Herman later developed the idea that the early universe was not only dense, but also incredibly hot. They predicted that as the universe expanded, this heat would leave behind a remnant glow, which we now know as the cosmic microwave background. The detection of the CMB in 1965 by Penzias and Wilson was a pivotal moment that lent strong empirical support to the Big Bang theory over the steady-state theory. The CMB's existence and properties were exactly what the Big Bang model predicted. The implications of these early universe theories were profound, challenging the notion of an eternal, unchanging cosmos and replacing it with a dynamic, evolving universe. Each theory contributed to a deeper understanding of our cosmos' very nature and its beginnings. From these beginnings, the field of cosmology has grown into a rigorous science, using the mathematical tools of general relativity and the observational data from astronomy to explore the universe's earliest moments. This exploration has not only provided insights into the nature of galaxies, stars, and planets, but also into the elements themselves. Understanding the universe's early conditions has allowed scientists to explain how the first elements were forged in the minutes following the Big Bang. As the Big Bang theory became more refined, it led to the development of the inflationary model, which proposes a rapid expansion of the universe in the first fractions of a second. This theory addresses several puzzles of the Big Bang theory, including the uniformity of the CMB across vast distances. Today, the study of the early universe continues to evolve, driven by both theoretical advances and new observations. Each discovery adds a piece to the puzzle, offering a clearer picture of how our universe came to be, from the most abstract theoretical physics to the most tangible astronomical observations. The Big Bang theory is the leading explanation about how the universe began. At its simplest, it talks about the universe as we know it starting with a small singularity, then inflating over the next 13.8 billion years to the cosmos that we know today. According to the Big Bang theory, the universe was once in an extremely hot and dense state which expanded rapidly. This expansion caused the universe to cool and resulted in its continuous expansion today. It is the attempt to explain what happened during and after that moment. Fundamentally, the Big Bang was not an explosion in space, but rather an expansion of space itself. Every part of the universe is moving away from every other part, with more distant objects moving away faster, leading to the initial formulation of Hubble's law. One of the many compelling pieces of evidence for the Big Bang is the ubiquitous presence of the cosmic microwave background radiation. This radiation is a remnant heat from the initial explosion of the Big Bang, acting as a snapshot of the infant universe. The theory suggests that in the first moments after the Big Bang, the universe was in a state of exceedingly high temperature and pressure. It expanded and cooled sufficiently for the first protons, neutrons, and electrons to form. As the universe continued to expand and cool, light elements like hydrogen and helium formed from the quarks and electrons via a process known as nucleosynthesis. This process occurred within the first few minutes of the universe's existence. The Big Bang theory also provides a framework for the cosmic timeline, from the initial moments where temperatures were billions of degrees, through the formation of basic particles, to the synthesis of light elements, and finally to the formation of stars and galaxies. This model of the universe's origin has been further refined by incorporating the concept of cosmic inflation. This theory posits that the universe underwent an exponential expansion in its first tiny fraction of a second, smoothing out and homogenizing the observable universe. Cosmic inflation helps explain several important puzzles of the Big Bang theory, such as why the universe appears flat, homogeneous, and isotropic when seen on a large scale. It also helps to explain the uniformity of the CMB. The Big Bang theory is supported by mathematical models and astronomical observations. Each observation and measurement made about the universe at large agrees with the predictions made by the Big Bang model concerning the observed abundances of the elements. As a framework, the Big Bang theory successfully explains the distribution of galaxies and the cosmic background radiation. It also accounts for the relative proportions of different elements in the early universe and the continuing expansion we observe today. Another evidence supporting the Big Bang theory is the abundance of helium, which is consistent with the predictions of a hot Big Bang nucleosynthesis model. About a quarter of the visible universe is helium, which would not be possible unless there was a state of high temperature and density, as the theory suggests. Moreover, the discovery of the expanding universe through redshift observations provides a direct observational foundation for this theory. It shows that galaxies are moving away from us in all directions, reinforcing the idea of an expanding universe. The Big Bang theory has become a critical pillar in cosmology because it provides the best explanation for the observations of astronomers and physicists. It ties together a wide variety of phenomena under a single theoretical framework. As research continues, the Big Bang theory is continually refined to incorporate new discoveries and observations, ensuring it remains a central concept in our understanding of the cosmic past and likely future developments in the universe. In the earliest moments following the Big Bang, the universe was incredibly hot and dense, much different from the vast and cold expanse we observe today. This initial state is often described as a singularity, where all the matter and energy of the cosmos were concentrated into an infinitesimally small point. As the universe began to expand, it did so exponentially in a phase known as cosmic inflation. This rapid expansion stretched the fabric of space itself, moving galaxies farther apart and decreasing the density and temperature of the universe dramatically. Following inflation, the universe continued to expand, but at a slower rate. This cooling allowed the first fundamental particles, such as quarks and electrons, to form. These particles later combined to create protons and neutrons. During the first few minutes of the universe, the process known as nucleosynthesis took place. During this period, temperatures finally cooled enough for the protons and neutrons to come together through nuclear fusion, forming the first nuclei of hydrogen, helium, and a small amount of lithium. This era, known as the recombination, occurred about 380,000 years after the Big Bang. At this point, electrons combined with nuclei to form neutral atoms. This allowed light to travel freely for the first time, as it was no longer scattered by free electrons, leading to the release of the cosmic microwave background radiation. The CMB radiation that we observe today is the afterglow of this recombination phase. It fills the entire universe and gives us a direct picture of what the cosmos looked like at this very early time, providing crucial information about the universe's initial conditions and its subsequent evolution. The universe's expansion can be observed through the redshift of light from distant galaxies. As space expands, light stretches and wavelengths lengthen. This shift towards the red end of the spectrum is directly proportional to the distance from Earth, confirming that the universe is still expanding. Gravitational effects continued to shape the universe as regions of slightly higher density attracted more matter. These fluctuations, initially tiny, grew over time due to the gravitational pull, eventually leading to the formation of stars, galaxies, and larger structures. This structure formation is a result of the cooling and clustering of dark matter and ordinary matter. Dark matter, invisible and not directly observable, interacts through gravity and forms the backbone for the development of complex structures. The cooling universe also set the stage for the formation of molecular clouds, the birthplaces of stars. As these clouds of gas and dust gathered, their increased density and gravity led to the formation of new stars and subsequently galaxies. The balance of forces such as gravity and the expansion of space is critical in shaping the universe. While gravity pulls matter together, the expansion of space can counteract these effects, influencing the rate and structure of formation in the cosmos. The universe's expansion is currently believed to be accelerating due to dark energy, a mysterious force that appears to be driving galaxies apart at an increasing rate. This observation suggests that the fate of the universe is intricately linked to the properties of dark energy. As the universe expands and evolves, it continues to cool, leading to new phases of cosmic evolution. This cooling trend impacts the life cycle of stars, the formation of planets, and potentially the future habitability of the universe. Through studying the expansion from a hot, dense state, scientists have developed models that predict not just the past behavior of the universe, but also its future. These models are crucial for understanding everything from the most fundamental particles to the largest galactic structures. The journey from a hot, dense state to the current expansive and structured universe is a remarkable story of transformation driven by physical laws. This narrative not only describes the universe's past, but also provides clues about its ultimate destiny. The prediction of the cosmic microwave background radiation is a cornerstone event in the history of cosmology, showcasing the predictive power of theoretical physics. It was initially foreseen as a necessary outcome of the hot Big Bang model of the universe. In the 1940s, George Gamow, a Soviet-American theoretical physicist, began exploring the implications of a hot, dense origin of the universe. He hypothesized that there should be some remnant radiation left over from this early state, which would provide direct evidence of the Big Bang. Alongside his colleagues Ralph Alpha and Robert Herman, Gamow calculated that this relic radiation would have cooled over the billions of years since the Big Bang, filling the universe with a faint glow of microwave radiation. Their calculations suggested that the temperature of this residual radiation would be about 5 degrees Kelvin. This was a bold prediction, as at the time, there was no observational evidence to support the existence of this cosmic afterglow. The theoretical work by Gamow, Alpha, and Herman laid the groundwork for what would later be known as the cosmic microwave background radiation. However, their predictions went largely unnoticed by the broader astronomical community for nearly 2 decades. It wasn't until the 1960s that the existence of the CMB was accidentally discovered by Arno Penzias and Robert Wilson. The pair were experimenting with a sensitive radio antenna when they stumbled upon a mysterious signal that was isotropic, not emanating from any specific source in the sky. Penzias and Wilson's discovery was initially a puzzle because the uniformity of the signal did not match any expected sources such as stars or galaxies. It took the intervention of a third party, Robert Dicke and his team, to realize that this was the predicted relic radiation from the Big Bang. Dicke had been preparing to search for the CMB himself, having independently come to the conclusion that it should exist based on his work in gravitational physics. The serendipitous discovery by Penzias and Wilson provided the missing empirical evidence confirming the Big Bang model. This detection of the CMB was one of the most significant confirmations of the Big Bang theory. It shifted the paradigm of cosmology from speculative and theoretical to one grounded in observable phenomena. The CMB's uniformity also offered a unique window into the conditions of the early universe, showing it to have been remarkably homogeneous. This was a critical piece of the puzzle in understanding how the cosmos evolved from simplicity to the complexity we observe today. Further studies on the CMB have continued to refine our understanding of the universe's origins. These investigations have measured the tiny fluctuations in the CMB's temperature that are the signatures of the initial density variations, which would eventually lead to the formation of galaxies. The precision mapping of these anisotropies has turned the CMB into a powerful tool for testing the conditions of the early universe against the predictions of the Big Bang theory and the theory of cosmic inflation. Every subsequent cosmic survey, from COBE to WMAP to Planck, has improved our understanding of the CMB, providing increasingly precise data about the universe's composition, age, and the process of cosmic evolution. Thus, the prediction and discovery of the cosmic microwave background not only bolstered the Big Bang model, but also opened up a new era of precision cosmology, where the foundations of the universe's grand structure are probed to an unprecedented degree. Ralph Alpha, George Gamow, and Robert Herman were pivotal figures in theoretical cosmology, especially regarding the prediction and understanding of the cosmic microwave background radiation. Their collaboration led to significant advancements in how we understand the early universe. George Gamow, originally a nuclear physicist, shifted his focus to cosmology and is best remembered for his work advocating the Big Bang theory. It was Gamow who first suggested that if the universe began in a state of high temperature and density, there should still be remnants of this initial heat. Ralph Alpha, a young physicist and a student of Gamow, took on the challenge of detailing these ideas. He was instrumental in developing the Big Bang nucleosynthesis theory, which predicted how the first elements were forged in the early moments of the universe. Together with Alpha, Robert Herman, who was also a physicist, calculated the expected temperature of residual radiation from the Big Bang. They predicted that the universe should be bathed in a faint glow of background radiation, cooling down to a few degrees above absolute zero. Their seminal work resulted in the Alpha-Herman-Gamow paper, often referred to simply as the AVG paper. This paper was groundbreaking as it predicted not only the synthesis of light elements during the Big Bang, but also the existence of the CMB, a fundamental aspect of the universe's evolution. Despite the brilliance of their predictions, Alpha and Herman's work on the CMB was not initially recognized, and their theoretical predictions went largely unnoticed by the broader scientific community until the accidental discovery of the CMB by Penzias and Wilson. Gamow's approach to science was characterized by a blend of deep insight and a penchant for playful and didactic storytelling. He was known for his ability to explain complex scientific ideas in accessible ways, which helped popularize the concept of the Big Bang. The collaboration between Alpha and Herman was marked by rigorous mathematical analysis and a deep understanding of thermodynamics and nuclear physics, which were critical in detailing the processes that occurred in the first minutes of the universe. Despite their significant contributions, it was not until the discovery of the CMB that the predictions made by Alpha, Hermann, and Gamow received the full recognition they deserved. This discovery confirmed their theoretical predictions and solidified the Big Bang theory as the leading cosmological model. Their work laid the foundation for all subsequent research into the cosmic microwave background and Big Bang nucleosynthesis, fields that have become central to modern cosmology. The trio's predictions also highlighted the importance of interdisciplinary collaboration in physics, drawing from nuclear physics, quantum mechanics, and astronomical observations to build a comprehensive picture of the universe's beginnings. Although overshadowed at times by more prominent figures in the field, the contributions of Alpha and Hermann have been reassessed in recent years, and they are now rightly considered as pioneers in cosmology. Their theoretical work has also helped establish many of the techniques used in modern cosmological research, particularly in the study of the universe's thermal history and the interpretation of CMB data. Looking back, the collaboration between Ralph Alpha, George Gamow, and Robert Hermann is a testament to the enduring value of theoretical predictions in science, proving that ideas well ahead of their time can eventually reshape our understanding of fundamental truths. In conclusion, the work of Alpha, Gamow, and Hermann not only paved the way for one of the most important discoveries in cosmology, but also continues to inspire current and future generations of scientists exploring the mysteries of the cosmos. The theoretical predictions of the cosmic microwave background, CMB, as a remnant of the early universe, were among the most profound insights into the nature of our cosmos. These predictions arose from a combination of theoretical physics and a deeper understanding of the universe's origins. When cosmologists first posited that the universe started from a hot, dense state, they inferred that after the Big Bang, the universe would have been filled with a sea of neutrons, protons, electrons, and photons. As the universe expanded, it cooled, leading to the formation of atoms and the release of photons. This sea of photons, initially in thermal equilibrium with matter, was predicted to cool down to just a few degrees above absolute zero as the universe expanded. These photons are what we now detect as the cosmic microwave background. The initial predictions suggested that this radiation would be isotropic and homogeneous, mirroring the supposed uniformity of the universe shortly after the Big Bang. The discovery of the CMB in the mid-20th century confirmed these predictions with remarkable accuracy. The temperature of the CMB, now measured at about 2.25 degrees above absolute zero, matches theoretical expectations derived from calculations based on the universe's rate of expansion and its cooling history. The presence of the CMB is considered a crucial test of the Big Bang theory. It provides a snapshot of the universe when it was only 380,000 years old, long before the first stars and galaxies formed, giving us direct evidence of the universe's conditions at that time. In theoretical terms, the CMB acts as a boundary condition for the universe's evolution. It helps cosmologists set initial conditions for models of cosmic structure formation and evolution. One of the more intriguing aspects of the CMB's prediction was the expectation of slight anisotropies or variations in temperature. These anisotropies were believed to reflect the density fluctuations in the early universe that would eventually lead to the formation of large-scale cosmic structures like galaxies and clusters. The detailed study of these temperature fluctuations, which was made possible by later satellite missions such as COBE, WMAP, and Planck, has provided insights into the distribution of matter and energy in the universe, including the nature and effects of dark matter and dark energy. These anisotropies also offer a window into the physics of the very early universe, potentially even hints about the epoch of inflation, an extremely brief period of rapid expansion that is hypothesized to have occurred fractions of a second after the Big Bang. The CMB's uniformity and the precision of its blackbody spectrum are significant because they offer strong support for the thermodynamic models of the early universe. These models assume that the early universe was in thermal equilibrium, a key concept in Big Bang nucleosynthesis. From a theoretical standpoint, the CMB also challenges physicists to explain its nearly perfect isotropy and homogeneity, given the causally disconnected regions it spans. This challenge has led to further support for inflationary theory, which proposes a mechanism to explain these observations. Overall, the theoretical predictions of the CMB underscore the predictive power of cosmological models and the laws of physics applied on cosmic scales. They illustrate how theoretical insights can lead to empirical discoveries that confirm and expand our understanding of the cosmos. In summary, the theoretical framework that predicted the CMB is a testament to the depth and scope of human curiosity and the relentless pursuit of understanding our universe's most fundamental aspects. The discovery of the cosmic microwave background, CMB, is a classic example of serendipity in scientific research. It underscores how unintended findings can lead to monumental shifts in our understanding of the universe. In 1964, Arno Penzias and Robert Wilson, two young radio astronomers at Bell Laboratories in New Jersey, were experimenting with a large horn antenna originally designed for satellite communications. Their goal was straightforward: to conduct radio astronomy observations and satellite communication experiments. However, Penzias and Wilson encountered a persistent background noise in their measurements, a faint microwave signal that was uniform and did not seem to originate from any known celestial source. This noise was present no matter where they pointed their antenna in the sky. Despite their best efforts to identify and eliminate potential sources of interference, including pigeon droppings in the antenna which they meticulously cleaned, the noise remained. It was unaccounted for by any of the usual suspects, such as urban radio interference or atmospheric effects. Puzzled by this noise, Penzias and Wilson reached out to other astronomers and physicists, seeking an explanation. It was a casual conversation with Bernard Burke of MIT that would steer them towards a groundbreaking realization. Burke recalled a lecture given by Robert Dicke at Johns Hopkins University, where Dicke proposed that a detectable microwave radiation permeated space as a remnant of the Big Bang. This suggestion immediately resonated with Penzias and Wilson's mysterious observations. Realizing the potential significance of their findings, Penzias and Wilson contacted Dicke, who, along with his colleagues at Princeton University, had been preparing an experiment specifically to search for this radiation. When Penzias and Wilson shared their data with Dicke, it became clear that they had already found the very signal Dicke and his team were seeking. This unintentional discovery provided the first direct evidence of the Big Bang theory. The impact of this discovery was profound. It provided the cornerstone evidence needed to solidify the Big Bang theory as the dominant cosmological model. Before this, the scientific community had been deeply divided between supporters of the Big Bang and the steady-state theories. The publication of Penzias and Wilson's findings in 1965, alongside a theoretical interpretation by Dicke's group, marked a pivotal moment in the field of cosmology. It shifted the paradigm and reshaped future research directions. For their accidental yet pivotal discovery, Penzias and Wilson were awarded the Nobel Prize in Physics in 1978. Their finding of the CMB has since been regarded as one of the most significant scientific discoveries of the 20th century. This discovery also spurred a new era of cosmology that focused on the precision measurement of the universe's background radiation, leading to a deeper understanding of the universe's early phases and its subsequent evolution. The legacy of this accidental discovery continues to influence cosmological research today. It paved the way for subsequent satellite missions like COBE, WMAP, and Planck, which have refined our measurements of the CMB and deepened our insights into the cosmos. Thus, the story of Penzias and Wilson is a testament to the unpredictable nature of scientific inquiry, where even the most unexpected results can lead to revolutionary understandings of our universe. Arno Penzias and Robert Wilson were two radio astronomers who inadvertently stumbled upon one of the greatest discoveries in the field of cosmology: the cosmic microwave background radiation, evidence of the universe's fiery beginnings. Their journey towards this discovery is as fascinating as the discovery itself. Penzias, born in Germany and having fled to the United States to escape Nazi persecution, found his passion in physics, eventually earning a PhD from Columbia University. His research interests led him to Bell Labs in New Jersey, an institution known for its innovative environment. Robert Wilson, an American with a keen interest in radio astronomy, joined Bell Labs after completing his graduate studies at the California Institute of Technology. There, he focused on radio technology and its astronomical applications, a field ripe with discovery potential. Together, Penzias and Wilson embarked on experiments using a large horn antenna that Bell Labs had originally built for satellite communication tests. Their initial aim was to probe the faint radio signals emitted by the Milky Way and other celestial bodies. While testing the antenna, they encountered a persistent, inexplicable noise, a soft static that seemed to emanate from every direction. This was unusual because such uniform noise was not characteristic of any known radio source from space. Despite extensive troubleshooting, including the removal of pigeon droppings from the antenna, the mysterious noise persisted. They meticulously examined every possible source of interference, from equipment malfunctions to atmospheric effects. Yet the noise remained. Frustrated but intrigued, Penzias and Wilson began consulting various experts in the field, searching for any explanation or precedent. It was during this quest that they were directed to a group of researchers at Princeton University who were exploring the theoretical aspects of cosmic radiation. This group, led by Robert Dicke, was theorizing about the remnant radiation from the Big Bang, which they hypothesized should permeate the universe. Dicke and his team were actually preparing their own experiment to search for this radiation. When Penzias and Wilson learned about Dicke's hypothesis, the pieces of the puzzle began to fall into place. They realized that the persistent noise they had been hearing might not be noise at all, but the very radiation Dicke's group was seeking. They reached out to Dicke, sharing their findings. Dicke immediately recognized the importance of their measurements, which aligned perfectly with his theoretical predictions about the Big Bang's leftover radiation. The collaboration that followed led to the simultaneous publication of Penzias and Wilson's observational results alongside Dicke's theoretical explanation. This pairing of theory and observation effectively solidified the Big Bang theory's standing in the scientific community. For their part in this landmark discovery, Penzias and Wilson were awarded the Nobel Prize in Physics in 1978. The recognition was a testament to the profound impact their accidental discovery had on our understanding of the universe. In subsequent years, both scientists continued their research in astronomy, contributing further to the field, though their discovery of the CMB remained the highlight of their careers. The story of Penzias and Wilson is not just a tale of scientific discovery, but also of perseverance and curiosity. It exemplifies how unexpected results, often dismissed as mere noise, can sometimes open doors to new realms of knowledge. Their journey from puzzling noise to Nobel Prize-winning discovery underscores the serendipitous nature of scientific inquiry, where even seemingly trivial anomalies can lead to monumental insights into the workings of the cosmos. Arno Penzias and Robert Wilson were utilizing a large horn-shaped antenna located at Bell Laboratories in Holmdel, New Jersey. This antenna, originally built for early satellite communication experiments, became the unlikely setting for a monumental discovery in cosmology. The antenna itself was designed to minimize radio noise, a crucial feature for their sensitive astronomical observations. It was able to detect microwaves at a wavelength of 7.35 centimeters, ideally suited for examining the galactic plane and other celestial phenomena. Their experimental setup was relatively straightforward. The antenna was connected to a low-noise radio receiver, which was crucial for picking up faint signals from space without adding significant interference of its own. During their experiments, Penzias and Wilson were continually troubled by a persistent background noise. This noise was isotropic, meaning it appeared to come uniformly from all directions in space, an unusual characteristic for celestial signals, which typically vary in intensity and origin. The noise exhibited a very specific blackbody temperature of about 3.5 Kelvin. Blackbody radiation is emitted by an object or environment that absorbs all radiation falling on it and re-radiates energy perfectly, a common theoretical concept in astrophysics. Despite their best efforts to identify and eliminate potential sources of interference, the noise persisted. They recalibrated instruments, checked for faults in the receiver, and even cleaned bird droppings from the antenna, thinking it might be affecting their data. The signal's uniformity was puzzling. It did not match the expected signatures from known sources like the Earth's atmosphere, distant galaxies, or the Milky Way. Everything from radio interference from nearby New York City to atmospheric effects was considered and ruled out. The anomaly was initially considered a nuisance, an unexplained artifact that might be stemming from their equipment. However, it was too consistent and stable to align with typical electronic glitches or external radio interference. The mystery deepened as they consulted with other experts in the field. No one could provide a satisfactory explanation for the noise that seemed to permeate the entire universe equally. It was only after speaking with Bernard Burke and Robert Dicke that Penzias and Wilson began to consider the possibility that their noise might be a significant scientific discovery. Dicke's group was actively looking for microwave radiation as a remnant from the Big Bang, which they theorized should fill the universe. Realizing the potential implications, Penzias and Wilson documented their findings meticulously, detailing the characteristics of the noise and their exhaustive efforts to rule out conventional explanations. Their documentation and eventual publication drew immediate attention from the scientific community. It matched theoretical predictions about the universe's thermal history, predictions that other scientists were beginning to make independently based on the Big Bang theory. The accidental nature of their discovery did not detract from its importance. Instead, it highlighted the serendipitous path of scientific discovery, where even unexpected or unwanted results can lead to significant breakthroughs. Their findings provided the first empirical evidence supporting the idea that the universe started from a singular, extremely hot and dense state, and has been expanding ever since. This realization was a turning point in cosmology, transforming theoretical concepts about the universe's origin into measurable science. Penzias and Wilson's experimental setup, although initially intended for more mundane astronomical observations, had inadvertently looked back nearly 14 billion years to the afterglow of the Big Bang. The interpretation of the anomalous signal detected by Penzias and Wilson was a crucial moment in the history of cosmology. Recognizing its significance required the theoretical framework that only a few scientists were considering at the time. Upon encountering the persistent microwave signal, Penzias and Wilson were initially at a loss. It was Robert Dicke's research group at Princeton University that provided the necessary theoretical interpretation, identifying the noise as the cosmic microwave background radiation from the Big Bang. Dicke had theorized that if the Big Bang had occurred, residual heat would be spread throughout the universe. This remnant heat from the early universe would appear as microwave radiation, uniformly filling the cosmos. The detection by Penzias and Wilson fit this description precisely. Dicke's group had been preparing to search for this background radiation themselves. When they heard of Penzias and Wilson's discovery, they immediately recognized it as the signal they had anticipated. This was a classic case of theory-meeting experiment in the scientific process. The confirmation of the CMB served as a major piece of evidence for the Big Bang theory, which posited that the universe had begun in an extremely hot and dense state and had been expanding ever since. Following the initial discovery and interpretation, other observations began to align with the existence of the CMB. Radio astronomers around the world started conducting similar experiments, which repeatedly confirmed the presence of the microwave background radiation. The uniformity of the CMB was particularly compelling. It suggested that the early universe had been in a state of thermal equilibrium, a condition necessary for the Big Bang model to hold true. Measurements of the CMB's spectrum revealed that it matched that of a perfect black body, a theoretical construct in physics that absorbs and re-emits all radiation at maximum efficiency. This was unlike any other astronomical source and aligned perfectly with predictions for the aftermath of the Big Bang. In subsequent years, the precision in measurements of the CMB increased dramatically. Satellite missions such as the Cosmic Background Explorer, COBE, and later the Wilkinson Microwave Anisotropy Probe, WMAP, provided detailed maps of the radiation, confirming its isotropic nature and detecting slight variations that corresponded to the early distribution of matter. These variations, or anisotropies, in the CMB provided a snapshot of the universe approximately 380,000 years after the Big Bang, before stars and galaxies had begun to form. They were crucial for understanding the large-scale structure of the universe. The study of the CMB has continued to evolve, with each new measurement refining our understanding of the universe's basic properties, such as its rate of expansion, age, and composition. Theoretical models of the universe were adjusted to incorporate the findings from CMB studies, leading to the development of the LCDM model, the standard model of Big Bang cosmology that includes dark matter and dark energy. The impact of the CMB on cosmology has been profound. It has not only confirmed aspects of the Big Bang, but has also helped cosmologists explore periods of the universe that are otherwise unreachable. The interpretation and confirmation of the CMB as a relic of the early universe represented a monumental achievement in astrophysics, turning abstract theoretical concepts into tangible elements of the observable universe. This process exemplifies the iterative nature of science, where observations lead to new theories, which in turn guide further observations, creating a deeper understanding of our cosmos. The story of the CMB is a testament to the power of scientific inquiry and collaboration across disciplines. The process by which the mysterious signal detected by Penzias and Wilson was identified as the cosmic microwave background, CMB, radiation, is a fascinating story of scientific deduction and collaboration. Initially, the significance of the uniform noise detected by their antenna was not clear to Penzias and Wilson. The duo knew they had encountered something peculiar, but the interpretation was beyond their immediate grasp. The turning point came through a serendipitous exchange with other researchers who were exploring theoretical aspects of the universe's origins. Bernard Burke of MIT informed Penzias of a lecture by Robert Dicker, who had hypothesized about the existence of microwave radiation as a relic of the Big Bang. Realizing the potential connection, Penzias contacted Dickey, who was working with a team at Princeton. This team included experts like Jim Peebles, who were already considering how to detect the afterglow of the Big Bang. Dickey and his team were astounded to learn about Penzias and Wilson's findings. They quickly surmised that the uniform microwave radiation the Bell Labs duo had been trying to eliminate was, in fact, the cosmic background radiation they were hoping to discover. To confirm that the signal was indeed the CMB, the characteristics of the radiation, such as its spectrum and isotropy, were carefully analyzed. The radiation displayed a perfect black body spectrum, which is consistent with the theoretical predictions of the Big Bang's remnant radiation. Furthermore, the uniformity of the radiation across the sky supported the idea that it originated from a time when the universe was hot and dense, a state expected shortly after the Big Bang before stars and galaxies had formed. This identification was bolstered by the temperature of the radiation. The CMB's temperature was measured at about 2.7 degrees Kelvin, closely matching the predictions made by earlier theorists like Alpha and Herman, who had calculated the Big Bang's residual heat would be a few degrees above absolute zero. The isotropic nature of the CMB also suggested that it was not influenced by objects within the galaxy or by the galaxy itself, indicating a cosmological origin that fit the profile for the Big Bang's afterglow. Once Penzias and Wilson understood what they had discovered, they prepared a paper detailing their observations. Simultaneously, Dickey's group prepared a theoretical paper explaining the cosmic origins and significance of the CMB. Both papers were published side by side in the Astrophysical Journal in 1965. This simultaneous publication linked the empirical observations with theoretical cosmology, providing strong evidence that the universe had indeed begun with a hot Big Bang. The identification of the CMB as the echo of the Big Bang was a major victory for the Big Bang theory, which had been competing with the steady-state theory up until that point. Subsequent experiments and observations have only reinforced the identification of the signal as the CMB. Each new piece of evidence has helped to refine our understanding of the universe's earliest moments and its subsequent evolution. The discovery and identification of the CMB fundamentally changed cosmology, transforming it into a precision science where hypotheses can be rigorously tested against observations. This breakthrough not only confirmed a major pillar of the Big Bang theory, but also set the stage for decades of cosmological research, focusing on understanding the composition and evolution of the universe from its very first moments. Robert Dicker was a pivotal figure in the theoretical understanding and eventual detection of the cosmic microwave background, CMB. His contributions extended beyond the theoretical predictions to fostering a collaborative atmosphere that accelerated the field of cosmology. Dickey's expertise in experimental physics and his interest in the fundamental forces of the universe drove him to speculate about the remnants of the Big Bang. He theorized that if the Big Bang had occurred, there would be residual background radiation permeating the universe. In the early 1960s, Dickey and a team at Princeton University, including David Wilkinson and Peter Roll, began building an instrument specifically designed to detect this microwave radiation. Their efforts were based on the prediction that the universe's expansion would leave behind a cooled, but still detectable signature of its explosive beginning. While Dickey did not initially discover the CMB, his theoretical framework and the detector he was developing were crucial in interpreting and confirming the significance of the noise Penzias and Wilson stumbled upon. Dickey's influence also extended to his students and colleagues. Jim Peebles, one of Dickey's doctoral students, played a significant role in developing the theoretical underpinnings of the Big Bang's radiation remnants. Peebles' work helped articulate how the radiation's properties could be used to glean information about the early universe's conditions. Another significant contributor was John Mather, who led the Cosmic Background Explorer (COBE) satellite project that provided detailed measurements of the CMB. Mather's work, which earned him a Nobel Prize, relied heavily on understanding and building upon the foundations laid by Dickey and his contemporaries. Philip James Edwin Peebles, often known as P.J.E. Peebles, made substantial contributions to cosmic background radiation studies and the theoretical framework of cosmology. His research helped refine the Big Bang model and deepen our understanding of the CMB's role in it. George Smoot, another key figure, was instrumental in the analysis of data from COBE. His work on the detailed texture of the CMB further validated the Big Bang model and provided deeper insights into the universe's texture at large scales. The collaboration between these scientists and many others illustrates the cumulative nature of scientific discovery. Dickey's initial hypotheses and the subsequent empirical discoveries by Penzias and Wilson set the stage for a series of advancements that would deepen and refine our understanding of the cosmos. Beyond his direct contributions to cosmology, Dickey also made significant advancements in the field of gravitational physics. His work helped pave the way for experiments testing Einstein's theory of general relativity, linking cosmology and quantum mechanics in new and profound ways. Dickey's legacy in cosmology is also marked by his emphasis on the importance of precision measurement and experiment in physics. He advocated for an approach that balanced theoretical exploration with empirical validation, a philosophy that has guided much of modern cosmology. The impact of Dickey and his colleagues' work on the CMB and cosmology cannot be overstated. They provided not only critical theoretical insights and predictions, but also spearheaded the development of technology and methods that continue to influence the field. Their efforts exemplify how theoretical physics and observational astronomy intersect, and how these disciplines complement each other to advance our understanding of the universe. Through their dedication and collaborative spirit, these scientists have left an indelible mark on the field of cosmology, transforming it into a dynamic and precise science that continues to challenge our understanding of the universe. Overall, the collective work of Dickey and others in this field has provided a robust framework that supports ongoing research into not only the origins of the universe, but also its ultimate fate. The Cosmic Background Explorer, commonly known as COBE, was a satellite launched by NASA in 1989. It was specifically designed to investigate the cosmic microwave background radiation, CMB, from the Big Bang and provide detailed measurements that could test theories about the early universe. COBE's mission was to measure the diffuse infrared and microwave radiation from the early universe to an unprecedented degree of accuracy. This was crucial for understanding the fundamental structure of the cosmos and the Big Bang theory. One of the primary instruments on COBE was the Differential Microwave Radiometer, DMR, which aimed to map the temperature fluctuations, or anisotropies, in the CMB. These minute variations in temperature tell the story of the early universe's matter distribution. Another significant instrument aboard COBE was the Far Infrared Absolute Spectrophotometer, FIRAS. This instrument was tasked with measuring the spectrum of the CMB, determining how closely it matched the theoretical prediction of a perfect black body. The data collected by FIRAS confirmed with astonishing precision that the CMB spectrum is indeed a nearly perfect black body spectrum. This was a significant triumph for the Big Bang model, confirming the universe did originate from a hot, dense state. COBE's findings on the CMB's anisotropies provided the first clear evidence of the ripples that would eventually lead to the formation of galaxies and large-scale structures. These fluctuations were critical for understanding how structures formed in the universe. The results from COBE revolutionized cosmology, turning what was once speculative into a precision science. Before COBE, the CMB had been detected, but its spectrum had not been measured with precision across a broad range of frequencies. John Mather and George Smoot, key figures in the COBE mission, were awarded the Nobel Prize in Physics in 2006 for their work related to the CMB measurements. Their findings had a profound impact on the confirmation of the Big Bang theory. COBE also carried out investigations into the cosmic infrared background, which provided insights into the process of galaxy formation and the evolution of the universe. These observations helped fill in the gaps about the universe's earliest stellar activities. The legacy of COBE extends beyond its scientific discoveries. It set a new standard for cosmological investigations, paving the way for future missions that would seek to explore the cosmic microwave background in even greater detail. Subsequent missions such as the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite built on COBE's legacy, refining the measurements of the CMB anisotropies and improving our understanding of the universe's content and history. The comprehensive data collected by COBE has been used to refine models of the universe's evolution, aiding theorists in understanding the complex dynamics that govern the cosmos. COBE's success demonstrated the importance of space-based instruments in cosmology, leading to a continued investment in space missions dedicated to understanding the universe's origin and structure. The impact of COBE on the field of cosmology cannot be overstated. It was not just a mission that confirmed certain aspects of the Big Bang, but a mission that opened up new avenues of inquiry in understanding the universe. Through its observations, COBE helped cosmologists and astronomers visualize the universe in its infancy, providing a clearer picture of how the cosmos has evolved over billions of years. The objectives of the Cosmic Background Explorer, COBE mission, were multifaceted, primarily designed to answer fundamental questions about the universe's composition and its evolution from the Big Bang to the present. COBE aimed to map the cosmic microwave background radiation, CMB, and search for large-scale anisotropies in its structure. COBE's first objective was to measure the CMB's spectrum with unprecedented precision. Scientists sought to confirm whether the CMB exhibited a perfect black body spectrum, a critical prediction of the Big Bang theory that had not been empirically verified before COBE. Another key objective was to map the fluctuations or anisotropies in the CMB. These temperature variations were believed to hold clues about the early universe's density fluctuations, which would eventually lead to the formation of galaxies and large cosmic structures. The differential microwave radiometers, DMR, aboard COBE, were tasked with mapping these temperature fluctuations across the sky, providing a clearer picture of the early universe's structure and the initial conditions that led to the formation of cosmic bodies. The Far-Infrared Absolute Spectrophotometer, FIRAS, on COBE aimed to measure the CMB's spectrum to verify its black body nature. This was crucial for validating the thermal history of the universe as predicted by the Big Bang model. COBE's findings were groundbreaking. FIRAS confirmed that the CMB spectrum is a nearly perfect black body, matching theoretical predictions with a precision that had never been achieved before. This finding alone significantly strengthened the case for the Big Bang theory. The DMR instrument found slight but significant anisotropies in the CMB. These variations in temperature were on the order of 1 part in 100,000, consistent with the theoretical predictions of the early universe's inhomogeneities. These anisotropies provided the seeds necessary for the formation of galaxies and larger structures under the influence of gravity. This was a pivotal discovery, linking the universe's large-scale structure to quantum fluctuations in the early universe. COBE's data also contributed to our understanding of the universe's geometry and rate of expansion. The measurements supported a flat universe, which has implications for theories of inflation and the total density of matter and energy in the cosmos. By confirming that the CMB has a black body spectrum, COBE helped rule out alternative cosmological models that predicted different kinds of early universe radiation. This placed the Big Bang theory on a much firmer empirical footing. The mission also investigated the cosmic infrared background, which provided insights into the processes of star formation and the evolution of galaxies over cosmic timescales. This helped astronomers piece together a more complete picture of the universe's history. The findings from COBE necessitated revisions and refinements in cosmological models, especially in terms of understanding how early universe conditions evolved into the complex structures observed today. The success of COBE sparked further interest and developments in cosmology, leading to subsequent missions with more advanced technology aimed at exploring the CMB in even greater detail. The legacy of COBE is not only in its scientific discoveries, but also in how it inspired a new generation of astronomers and physicists to explore the universe's earliest moments and its largest scales. Overall, COBE's objectives and findings significantly enhanced our understanding of the universe, marking a new era in cosmology, where empirical data could be used to test and refine theoretical predictions about the cosmos. The significance of COBE's findings on the uniformity and spectrum of the cosmic microwave background radiation cannot be overstated. These findings have played a critical role in shaping our understanding of the universe's origins and its fundamental properties. By confirming that the CMB has a nearly perfect black-body spectrum, COBE provided one of the most significant pieces of evidence for the Big Bang theory. This confirmation implied that the early universe was in a state of thermal equilibrium, a key assumption of the Big Bang model. The precision with which COBE measured the CMB's spectrum helped resolve ongoing debates in cosmology regarding the nature of the early universe. It firmly established that the universe began from a hot, dense state and has been cooling and expanding ever since. COBE's measurements of the uniformity of the CMB across the sky demonstrated that, on large scales, the universe is remarkably homogeneous. This uniformity is a cornerstone prediction of the cosmological principle, which posits that the universe is isotropic and homogeneous when viewed on a large enough scale. However, COBE also detected slight variations or anisotropies in the CMB. These anisotropies are incredibly subtle, on the order of 1 part in 100,000, yet they hold immense significance for cosmology. These small temperature fluctuations reveal the initial seeds of structure in the universe. They correspond to tiny density variations in the early universe, which under the influence of gravity grew into galaxies, clusters of galaxies, and the vast cosmic web observed today. The anisotropies confirmed the theory of inflation, which proposes that the early universe underwent a rapid exponential expansion. This theory explains the observed flatness and uniformity of the universe and predicts the kinds of fluctuations that COBE observed. COBE's findings also provided a foundation for the LCDM model, the standard model of cosmology that includes dark matter and dark energy. This model describes the universe's overall geometry, composition, and the evolution of its structure from the Big Bang to the present. The data from COBE has been used extensively to constrain the parameters of the LCDM model, such as the Hubble constant, the density of baryons, the density of dark matter, and the spectral index of primordial fluctuations. These measurements have important implications for particle physics, particularly theories about the types and properties of particles that were present in the early universe and may still exist as dark matter. From a technological perspective, COBE's achievements demonstrated the capabilities of space-based astronomical instruments. The success of COBE led directly to the development and launch of more advanced CMB observation missions, such as the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite. Educationally, COBE's findings have enriched the content of astrophysics and cosmology courses worldwide, providing new material and data for academic study and research. The societal impact of COBE's discoveries extends to a deeper philosophical understanding of our place in the universe. By providing a clearer picture of the universe's origin, COBE has influenced our perception of humanity's place in the cosmos. The cultural significance of understanding the universe's beginnings also cannot be ignored. COBE's findings have penetrated popular science and become a part of the broader public conversation about science and the universe. In summary, COBE's findings regarding the uniformity and spectrum of the CMB have fundamentally altered the landscape of cosmology, leading to a more precise and profound understanding of the universe's structure, origins, and ultimate fate. The Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, represented a significant advancement in the study of the cosmic microwave background, CMB. Building on the discoveries of COBE, WMAP was designed to provide a more detailed map of the CMB and thereby enhance our understanding of the universe's geometry, composition, and evolution. WMAP's primary mission was to measure the temperature fluctuations in the CMB with higher resolution, sensitivity and accuracy than its predecessor, COBE. These measurements are crucial for understanding the underlying physics of the early universe and the fundamental forces that shaped its development. The data collected by WMAP has been instrumental in refining the values of several key cosmological parameters, including the age of the universe, the density of atoms, the density of matter, and the density of dark energy, which drives the accelerated expansion of the universe. One of the landmark findings from WMAP was the precise determination of the age of the universe at approximately 13.77 billion years. This measurement provided a more accurate timeline for the evolution of cosmic structures. WMAP also confirmed with greater precision that the universe is flat with only a 0.4% margin of error. This flatness has profound implications for the fate of the universe and supports inflationary models of the early universe. The detailed maps produced by WMAP revealed richer textures of the CMB anisotropies. These textures provide insights into the distribution of matter and energy when the universe was just 380,000 years old, offering clues about the seeds of cosmic structure. WMAP's data supported the existence of a standard model of cosmology, the Lambda Cold Dark Matter (LCDM) model, which includes dark energy as a significant component of the universe's current energy budget. The probe's observations have helped to solidify the theory of inflation, confirming that the distribution of temperature fluctuations in the CMB is consistent with this model. Inflation describes the rapid expansion of the universe moments after the Big Bang, smoothing out any irregularities. Furthermore, WMAP provided new insights into the epoch of rionization, the period when the first stars and galaxies formed and ionized the intergalactic medium. According to WMAP data, rionization occurred about 400 million years after the Big Bang. WMAP's measurements of the polarization of the CMB further enriched our understanding of the universe. Polarization data help map the motion of light from the early universe and provide a three-dimensional look at the cosmos at its infancy. The precision of WMAP's data also constrained the theories about the nature and effects of neutrinos in the universe. It suggested that neutrinos make up a small but significant portion of the universe's total mass energy content. The satellite's findings played a crucial role in advancing the concept of cosmic neutrino background and hinted at neutrino oscillations, phenomena that are key to understanding fundamental particle physics. WMAP's mission extended well beyond its expected duration, providing a wealth of data over 9 years before its retirement in 2010. Each release of data from WMAP refined our cosmological models and provided new fodder for theoretical investigation. The legacy of WMAP continues to influence contemporary cosmology. Its data is still used by researchers worldwide to challenge and refine theoretical models of the universe. In conclusion, WMAP has not only deepened our understanding of the cosmos, but has also raised new questions about the universe's earliest moments, composition, and ultimate fate. It stands as a testament to the power of detailed observation to reshape our cosmic perspectives. The primary goals of the Wilkinson Microwave Anisotropy Probe, WMAP, were to provide a detailed map of the cosmic microwave background, CMB radiation, to determine the geometry, content, and evolution of the universe, and to test the predictions of the Big Bang model and inflationary theory. WMAP aimed to measure the temperature differences across the sky in the CMB with unprecedented accuracy. This data would enable scientists to learn about the distribution of matter and energy in the early universe, thus helping to construct a detailed timeline of cosmic evolution. One of the key discoveries of WMAP was the precise determination of the universe's age, estimated at 13.77 billion years, with an error margin of less than 1%. This was a more accurate measure than previous estimates and critical for calibrating other cosmological models. WMAP data confirmed that the universe is flat with a density very close to the critical density needed to stop the universe from collapsing in on itself. This has major implications for understanding the fate of the universe and supports the inflation model, where the universe underwent rapid expansion moments after the Big Bang. The probe's detailed observation of the CMB anisotropies provided more evidence for the existence of dark energy, a mysterious force that is driving the accelerated expansion of the universe. Dark energy was found to make up approximately 71.4% of the universe's total energy content. WMAP also clarified the proportions of other key components of the universe, finding that dark matter constitutes about 24% and ordinary baryonic matter about 4.6%, altering previous estimates and providing a clearer picture of the universe's composition. The data from WMAP supported the lambda cold dark matter (LCDM) model, which has become the standard model of Big Bang cosmology. This model describes a universe dominated by dark energy, lambda, and cold dark matter, fitting the WMAP data remarkably well. Another significant achievement of WMAP was the measurement of the polarization of the CMB. This measurement provided insights into the epoch of rionization, when the first stars ionized the primordial gas, a key phase in the history of the universe. WMAP's observations contributed to refining the scale of cosmic inflation, providing evidence that the distribution of fluctuations in the CMB is consistent with the predictions of inflationary models. This evidence supports the idea that the universe expanded exponentially during its first fractions of a second. The probe's findings helped solidify the timeline for cosmic events, such as when the first stars began to shine. According to WMAP, Rionization began about 400 million years after the Big Bang, earlier than previous estimates suggested. WMAP's results also constrained the models of cosmic structure formation, showing how quantum fluctuations in the early universe developed into the large-scale structures seen today. The data refined our understanding of the shape and texture of the universe's anisotropies, which helped cosmologists understand gravitational forces at work in the early cosmos and how they led to galaxy formation. WMAP's measurements of the temperature fluctuations in the CMB provided a deeper understanding of the seeds from which all cosmic structures grew, helping to explain the universe's large-scale structure as observed today. The satellite's comprehensive map of the CMB remains one of the most important tools for cosmologists, offering a detailed image of the universe when it was only 380,000 years old, and providing a foundation for future explorations of the cosmic background radiation. Overall, the goals and discoveries of WMAP have greatly enhanced our understanding of the universe, providing not only confirmation of many aspects of the Big Bang model, but also offering new insights that continue to influence cosmological thought and research. The Wilkinson Microwave Anisotropy Probe, WMAP, played a crucial role in refining our understanding of the age and composition of the universe, marking a significant advancement in cosmology. Through its precise measurements of the cosmic microwave background, CMB, WMAP provided data that clarified several key cosmological parameters. WMAP's detailed observations of the CMB anisotropies allowed cosmologists to calculate the age of the universe with unprecedented accuracy. Prior to WMAP, estimates varied, but WMAP data pinpointed the universe's age at about 13.77 billion years, with a remarkably low margin of error. This precise measurement was possible because the fluctuations in the CMB hold information about the rate of expansion of the universe. By understanding these fluctuations, WMAP helped apply and refine the calculations of the Hubble constant, which measures the universe's expansion rate. WMAP's findings also significantly impacted our understanding of the universe's composition. By measuring the curvature of the universe through the CMB data, WMAP provided strong evidence that the universe is flat. A flat universe suggests that the total density of matter and energy in the universe is close to the critical density needed to halt its expansion. The probe's observations confirmed that ordinary matter, the stuff making up stars, planets, and galaxies, constitutes only about 4.6% of the universe's total mass energy content. This was a more precise measurement than previous estimates, and has implications for understanding the formation and evolution of cosmic structures. WMAP also provided detailed measurements confirming the existence and quantity of dark matter, an invisible substance that does not emit light or energy. According to WMAP, dark matter constitutes about 24% of the universe, helping to explain the gravitational forces that hold galaxies together. Perhaps most significantly, WMAP data underscored the dominance of dark energy, a mysterious force driving the accelerated expansion of the universe. WMAP estimated dark energy to make up about 71.4% of the universe, aligning with and refining previous observations from supernovae studies. The probe's analysis of the CMB also included measurements of its polarization, which helped refine models of the universe's total energy content and distribution. This polarization data provided further insights into the universe's early stages and its rate of expansion. Through its comprehensive mapping of temperature fluctuations across the sky, WMAP data helped cosmologists fine-tune the lambda cold dark matter (LCDM) model, which is the standard theoretical model of cosmology. This model now includes precise proportions of dark energy, dark matter, and ordinary matter. WMAP also shed light on the epoch of rionization, the period when the first stars and galaxies ionized the surrounding medium. By analyzing the polarization and temperature data, WMAP suggested that rionization occurred about 400 million years after the Big Bang, earlier than some previous estimates. The insights gained from WMAP extended to the inflationary theory of the universe. The patterns observed in the CMB fluctuations were consistent with the predictions of inflation, supporting the theory that the universe underwent a rapid expansion shortly after the Big Bang. Furthermore, WMAP's detailed cosmic measurements have played a critical role in supporting the cosmological principle, which posits that the universe is homogeneous and isotropic when viewed on a large enough scale. The contributions of WMAP to cosmology have had a lasting impact on the field, providing a cornerstone of evidence for many theoretical models and sparking new lines of inquiry into the fundamental nature of the cosmos. In summary, WMAP not only refined our understanding of the universe's age and composition, but also deepened our insight into the physical processes underlying the universe's evolution from its earliest moments to the present day. The legacy of WMAP continues to influence contemporary astrophysics, providing a foundation for future explorations aimed at unraveling the complexities of the universe. Through its revelations, we have gained a more coherent and detailed understanding of our cosmic environment. The Planck satellite, launched by the European Space Agency in 2009, was designed to continue the exploration of the cosmic microwave background, CMB, initiated by earlier missions like COBE and WMAP. With more advanced technology, Planck aimed to provide a more detailed map of the CMB and further refine our understanding of the universe's composition and evolution. Planck was equipped with a higher resolution and sensitivity compared to its predecessors, enabling it to measure the CMB across a wider range of microwave frequencies. This capability allowed Planck to detect both the temperature and polarization of the CMB with unprecedented precision. One of Planck's primary goals was to test and improve upon the cosmological models established by earlier missions. By providing more precise data, Planck helped to tighten the constraints on the parameters of the standard model of cosmology, the lambda cold dark matter (LCDM) model. Planck's observations offered new insights into the inflationary period of the early universe. The satellite's data provided evidence supporting the theory that the universe underwent a rapid expansion just fractions of a second after the Big Bang, smoothing out any irregularities and leading to the homogeneous universe observed today. Additionally, Planck's findings refined measurements of the CMB's anisotropies, tiny variations in temperature that represent the seeds of future cosmic structure. These detailed measurements have been crucial for understanding the distribution of matter and energy in the early universe. Planck also made significant contributions to the study of dark matter and dark energy, two of the most mysterious components of the universe. The satellite's data helped clarify their influence on the universe's structure and expansion rate. Through its observations, Planck challenged some aspects of the inflationary model, finding certain anomalies in the CMB that were not predicted by standard theories of cosmology. These anomalies included a slight asymmetry in the CMB's temperature distribution across the sky and a cold spot that appeared larger than expected. The detailed maps produced by Planck allowed astronomers to trace the universe's history more accurately from the Big Bang to the present day. This comprehensive view is essential for testing theories about the universe's rate of expansion and the growth of cosmic structures. Planck's mission also enhanced our understanding of the cosmic neutrino background and the number of neutrino species, which play a critical role in the thermal history of the universe. This was a significant advancement for both cosmology and particle physics. Furthermore, Planck investigated the cosmic infrared background radiation, which provides information about the earliest stars and galaxies. This exploration helped fill in gaps about the universe's stellar evolution and the formation of large-scale structures. The Planck satellite's data repository has become a valuable resource for scientists worldwide, offering a wealth of information that continues to be analyzed and interpreted in various research projects. Planck's findings have necessitated some revisions in the theoretical framework of cosmology, prompting discussions and further studies aimed at resolving the small but significant discrepancies between observations and model predictions. The legacy of Planck extends beyond its contributions to cosmology, impacting fields such as astrophysics and fundamental physics. The mission has provided a deeper understanding of the universe, influencing theories about gravity and the fundamental forces of nature. In conclusion, the Planck satellite has significantly advanced our knowledge of the cosmic microwave background and the early universe. Its precise measurements have refined our cosmic models, challenged existing theories, and opened new avenues for understanding the universe's most fundamental aspects. The success of Planck exemplifies the importance of continual technological advancement and international cooperation in the quest to explore the cosmos and unravel the mysteries of the universe. Planck's mission was crafted to delve deeper into the cosmic microwave background, CMB, than any previous satellite, including its predecessors COBE and WMAP. Its design was focused on achieving high sensitivity and angular resolution across a wider frequency spectrum, enabling a more detailed view of the universe's earliest light. One of the key improvements Planck offered over previous probes was its ability to measure the CMB at 9 different frequency bands. This range allowed Planck to effectively separate the CMB signal from foreground emissions caused by dust, synchrotron radiation, and other sources within our galaxy. Planck was equipped with 2 primary scientific instruments, the low-frequency instrument, LFI, which operated between 30 and 70 GHz, and the high-frequency instrument, HFI, which covered higher frequencies from 100 to 857 GHz. This setup provided a broader spectral coverage compared to WMAP's 5 frequency bands, enhancing the accuracy of cosmological measurements. The satellite's instruments were cooled to temperatures near absolute zero to minimize noise and maximize sensitivity. The HFI, for example, was cooled to just 0.1 degrees above absolute zero, the coldest temperature achieved in space at the time, allowing for extremely precise measurements of the CMB's tiny temperature fluctuations. Planck's higher resolution allowed it to observe features as small as 1/10 of a degree on the sky, which is about twice the angular size of the full moon. This capability enabled Planck to detect subtler fluctuations in the CMB than WMAP could, providing new insights into the properties of the early universe. The precision of Planck's measurements helped to refine our understanding of the universe's composition and the physics of the early universe, including more stringent constraints on the parameters of the lambda cold dark matter, LCDM model. These parameters include the Hubble constant, the density of dark matter, and the density of dark energy. Planck also improved our knowledge of the universe's age, refining the estimation to about 13.8 billion years with a greater degree of accuracy. This adjustment was based on more precise measurements of the CMB's anisotropies and the universe's overall curvature. By providing a clearer picture of the polarization of the CMB, Planck added another layer of data to our understanding of the early universe. Polarization measurements are sensitive to the ionization history of the universe and the physics of the inflationary period, areas where Planck made significant contributions. Furthermore, Planck's data allowed scientists to test theories of cosmic inflation in detail. The observations were consistent with the simplest inflation models, where the quantum fluctuations in the early universe became the seeds for all future structure formation. The mission also offered new insights into anomalies in the CMB's temperature field. These included features like the cold spot and the slight asymmetry in temperature fluctuations, which continue to challenge the standard model of cosmology and spur theoretical developments. Planck's ability to measure the isotropic background light not associated with stars, light from the earliest phases of star formation, provided valuable clues about the process of structure formation in the universe. The satellite confirmed that the first stars ignited about 550 million years after the Big Bang, sharpening our understanding of the timeline for when the universe first became ionized. Planck's findings contributed to adjustments in the scale of cosmological perturbations, refining the spectral index of primordial fluctuations. This measurement is crucial for understanding the density fluctuations that gave rise to the universe's structure. Through its mission, Planck provided a wealth of data that continues to be analyzed, offering potential breakthroughs in areas such as the nature of dark matter and the properties of neutrinos. In summary, Planck's mission represented a significant leap forward in cosmic microwave background research. Its advanced instruments and broader frequency coverage provided a more detailed and comprehensive map of the early universe, surpassing previous probes and deepening our understanding of the cosmos's foundational properties. Planck's detailed observations of the cosmic microwave background, CMB, provided profound insights into the early universe, particularly regarding the phenomenon known as cosmic inflation. These findings have helped to refine our understanding of how the universe evolved from its earliest moments. Cosmic inflation is a theory that suggests the universe underwent a rapid exponential expansion in the fractions of a second following the Big Bang. This expansion smoothed out any irregularities and homogenized the properties of the universe at the largest scales. Planck's data confirmed several key predictions of inflationary theory, including the almost perfect scale invariance of the temperature fluctuations in the CMB. This characteristic indicates that the primordial fluctuations were consistent across different scales, a hallmark of the inflationary model. The satellite also measured the slight deviations from perfect scale invariance, known as spectral tilt. This finding was crucial, as it supported the idea that the density fluctuations in the early universe were not exactly the same at all scales, which is predicted by the simplest models of inflation. Furthermore, Planck helped to solidify the understanding of the polarization of the CMB. Polarization measurements are sensitive to the primordial light scattering by electrons, and Planck's data provided additional support for the theory that the universe became Rayonized about 550 million years after the Big Bang. Planck's observations also addressed the anomalies observed in previous CMB data, such as the slightly larger temperature fluctuations at large angular scales. While these anomalies remain not fully explained, Planck's high-precision data has been crucial in determining whether they point to new physics or arise from cosmic variance. One of the intriguing aspects of Planck's findings was the confirmation of the presence of gravitational lensing in the CMB. This phenomenon occurs when massive objects bend the path of CMB photons, which can help map the distribution of mass across the universe and provide evidence for the existence of dark matter. The detailed data from Planck also constrained the number of relativistic species, such as neutrinos, in the early universe. This has implications for particle physics, providing a critical link between cosmology and fundamental particles. Planck's findings have led to tighter constraints on the energy scale of inflation, suggesting a lower energy level than some previous estimates. This has implications for the theories of unification of the fundamental forces, which are predicted to come into play at high energy scales. Additionally, Planck's data has been used to test alternatives to the standard model of inflation, including models that propose different behaviors for inflation at different times or under different conditions. The satellite's comprehensive survey of the CMB provided a more accurate determination of the optical depth due to rayonization, which measures the thickness of the fog of ionized photons in the universe. This measurement is vital for understanding the timing and process of reionization. Planck's findings have contributed to a better understanding of the isotropy of the CMB. Despite the universe's large-scale uniformity, Planck confirmed that there are statistically significant anisotropies that need to be reconciled with current cosmological theories. Through its mission, Planck has also contributed to the debate about the exact shape of the universe. Its data suggests a flat universe, but with a level of precision that continues to challenge cosmologists to improve models and measurement techniques. The wealth of data from Planck has led to numerous studies and will continue to be a cornerstone of cosmological research. Its legacy will endure through the ongoing analysis and the continued refinement of our cosmological models. In conclusion, the Planck satellite has provided detailed findings that have significantly advanced our understanding of the CMB and cosmic inflation, helping to answer fundamental questions about the universe's composition, its earliest moments, and its long-term fate. Our understanding of the early universe has been dramatically reshaped by the wealth of data provided by observations of the cosmic microwave background, CMB. These insights offer a clearer picture of how the universe evolved from its nascent moments into the complex cosmos we observe today. The CMB serves as a fossil of the universe's infancy, a snapshot of a time just 380,000 years after the Big Bang, when the cosmos transitioned from opacity to transparency. This period marked the release of photons, which we now detect as the CMB, providing direct evidence of the universe's conditions at that time. One of the key aspects of studying the early universe involves examining the slight irregularities in the CMB. These temperature anisotropies are indicators of density fluctuations that eventually led to the formation of all cosmic structures, from galaxies to large-scale superclusters. Understanding the early universe also involves exploring the concept of inflation, a rapid expansion that is thought to have occurred fractions of a second after the Big Bang. This theory helps explain the uniformity and flatness observed in the universe, solving several problems in the Big Bang model. Data from various CMB observations have supported the idea that the early universe was remarkably homogeneous and isotropic, confirming the cosmological principle that suggests the universe is uniform when viewed on a large scale. The polarization patterns observed in the CMB also provide insights into the universe's first moments. These patterns are influenced by gravitational waves, ripples in space-time, that would have been generated during inflation, offering a potential window into quantum gravitational effects. Studies of the CMB have also led to better constraints on the types of matter and energy that filled the early universe. For instance, precise measurements of the CMB have helped clarify the role and amount of dark matter and dark energy, which together compose most of the universe's total density. The temperature of the CMB, which is remarkably consistent across the sky, has been measured with incredible precision, and slight deviations from this temperature help cosmologists determine the rate of expansion of the universe since its birth. Cosmological models refined by CMB data suggest that the universe underwent a period of reionization approximately 550 million years after the Big Bang. This was when the first stars ignited, adding enough energy to reionize the surrounding medium, which had cooled and formed neutral atoms during recombination. The details gleaned from the CMB also inform our understanding of the fundamental forces and particles in play during the early universe. This is pivotal for integrating cosmology with particle physics and understanding how the early universe acted as a natural particle accelerator. Furthermore, the synthesis of light elements in the early universe, a process known as nucleosynthesis, is closely tied to our understanding of the CMB. The relative abundances of hydrogen, helium, and lithium observed today align with predictions based on the temperature and density conditions inferred from the CMB. Understanding the early universe also challenges physicists to explain anomalies and irregularities in the CMB that standard cosmological models do not predict. These include certain asymmetries and cold spots that hint at new physics or complex phenomena not yet understood. The continuous improvement in technology and methods for observing the CMB promises even deeper insights into the early universe. Future missions aim to measure the CMB with even greater accuracy, potentially revealing more about the initial conditions that shaped the cosmos. By piecing together this information, cosmologists are not only mapping the history of the universe, but are also testing the limits of physical laws under conditions that cannot be replicated in any laboratory on Earth. In summary, our understanding of the early universe, largely derived from the study of the CMB, continues to evolve as new data emerge. Each discovery adds a piece to the puzzle, refining our picture of how the universe began and how it has changed over billions of years. Studies of the cosmic microwave background, CMB, are pivotal for cosmology because they provide a direct image of the universe just 380,000 years after the Big Bang, much before the formation of stars and galaxies. This picture reveals conditions from a time when the cosmos was drastically different from what we see today. The uniformity of the CMB, with its slight fluctuations, supports the Big Bang theory, confirming that the universe was once in a hot, dense state. As the universe expanded, this heat left behind a glow that fills the entire universe, and studying this afterglow gives us a foundational view of the cosmos's early moments. Temperature fluctuations in the CMB are particularly valuable, as they represent the seeds of all current structures in the universe. These tiny variations in density were critical for the formation of galaxies and large-scale structures under the influence of gravity. The precision measurement of these fluctuations by missions like COBE, WMAPI, and Planck has allowed cosmologists to calculate the age of the universe more accurately, estimate the rate of its expansion, and infer the makeup of the cosmos, including the relative amounts of normal matter, dark matter, and dark energy. CMB studies have also provided evidence for the inflationary theory, which posits that the universe underwent a rapid exponential expansion in the first tiny fraction of a second. This theory explains the uniformity and flatness of the universe and predicts the statistical pattern of temperature fluctuations observed in the CMB. The scale-dependent fluctuations in the CMB have been used to test different models of inflation, helping physicists understand not just when inflation occurred, but also how it happened and what drove it. This is crucial for connecting the physics of the very small, like particles, with the physics of the very large, like galaxies. CMB research has further refined our understanding of the cosmological principle that on large scales the universe is homogeneous and isotropic. The CMB's uniformity across the sky is a strong testament to this principle, suggesting that the same physical laws apply throughout the universe. Through polarization studies, scientists examine how light from the CMB was scattered by electrons in the early universe, offering clues about the universe's ionization. This was the era when the first stars and galaxies ionized the neutral hydrogen that was present throughout the universe after the era of recombination. Moreover, CMB data has been instrumental in studying gravitational lensing effects, where light from the CMB is bent around massive objects. This phenomenon helps map the distribution of mass across the universe, providing indirect evidence of dark matter. The CMB also serves as a cosmological backdrop against which the motion of our local group of galaxies is measured. This helps in understanding our galaxy's trajectory through space and provides context for the dynamic behaviors observed in our cosmic neighborhood. CMB studies have implications for fundamental physics, testing theories of gravity and the nature of the early universe. Variations in the CMB data can hint at physics beyond the standard models of cosmology and particle physics, prompting new theories and experiments. Additionally, the integration of CMB data with other astronomical observations, like galaxy surveys, enhances our understanding of cosmic evolution from the universe's first moments to its current state, creating a comprehensive picture of cosmic history. This synergy between CMB observations and other cosmological data is also key in addressing anomalies and irregularities in the cosmic background radiation. These may reveal aspects of the universe that are not yet understood, challenging existing theories and suggesting new physics. Each advancement in CMB research brings us closer to answering fundamental questions about the universe. How did it begin? What is it made of? How will it evolve? These studies not only deepen our understanding of the cosmos, but also of the laws of physics that govern everything. In conclusion, studies of the CMB are essential for constructing a detailed narrative of the universe's first moments, providing a window into the past that allows scientists to reconstruct the history and evolution of the cosmos with remarkable precision. Cosmic inflation, a theory proposed to explain the uniformity and flatness of the universe, suggests that the universe underwent a rapid exponential expansion shortly after the Big Bang. This phase smoothed out any irregularities and distributed energy uniformly across the early universe, which is reflected in the cosmic microwave background, CMB, we observe today. The minute temperature fluctuations in the CMB are a direct outcome of inflation. These fluctuations represent the initial slight irregularities in the universe's density that were magnified by inflation. They provide a unique snapshot of the universe at its earliest, allowing cosmologists to map the seeds of cosmic structures. These primordial fluctuations are believed to have grown under the influence of gravity to form all the structures in the universe, from galaxies to clusters and superclusters. The detailed pattern of these fluctuations captured by the CMB is key to understanding how complex structures emerge from a nearly uniform beginning. The study of inflation also involves exploring the physics of the very early universe, potentially linked to theories of quantum gravity. Insights into inflation come from examining the scale dependence of the fluctuations in the CMB, which tell us how different regions of space expanded. The polarization of the CMB, which Planck and other missions have measured, provides additional clues about inflation. Polarization is caused by the scattering of light in the early universe and can be influenced by gravitational waves, ripples in space-time produced during inflation. Gravitational lensing of the CMB, another phenomenon studied through these observations, helps map the total matter distribution in the universe, including dark matter, which does not emit light. This lensing effect confirms that large-scale structures grew over billions of years from the small fluctuations left by inflation. Cosmic inflation predicts a nearly Gaussian distribution of temperature fluctuations, which has been confirmed by CMB observations. This agreement between theory and observation is a strong endorsement of the inflationary model. However, the exact mechanism driving inflation remains one of the biggest questions in cosmology. The energy scale of inflation, linked to the potential of the inflaton field, thought to be responsible for inflation, is still a topic of active research and debate. As structures formed in the universe, the gravitational attraction of matter led to the growth of perturbations. Overdense regions pulled in more matter, growing larger over time, while underdense regions became voids. This process is well documented by simulations that match CMB observations. The interaction between dark matter and normal matter also plays a crucial role in the growth of cosmic structures. Dark matter, which does not interact with electromagnetic forces, forms the backbone of galaxies and clusters by gravitationally attracting normal matter. Advanced CMB studies also hint at the existence of features that standard inflationary models do not predict, such as certain anisotropies and cold spots. These features suggest potential extensions or alternatives to the simplest inflationary models, possibly involving multiple fields or interactions. The synthesis of light elements in the early universe, a process known as Big Bang nucleosynthesis, is closely tied to our understanding of inflation. The relative abundances of hydrogen, helium, and other light elements depend on the conditions set by inflation and are consistent with CMB measurements. Future observations and experiments aim to probe the polarization of the CMB more deeply to detect signatures of gravitational waves from inflation. Such discoveries could provide the smoking gun evidence for inflation and offer insights into the energy scale at which inflation occurred. By continuing to study the CMB and its implications for cosmic inflation and the growth of structures, cosmologists hope to answer fundamental questions about the universe, such as why it appears to be so homogeneous on large scales, and what drove its initial expansion. In conclusion, the insights into cosmic inflation and the growth of cosmic structures derived from CMB studies not only strengthen our understanding of the universe's early moments, but also continue to challenge and refine our models of cosmic evolution. The exploration of the cosmic microwave background, CMB, has not only solidified our understanding of the universe's basic structure and origins, but also presented several mysteries and anomalies that continue to challenge existing cosmological models. These peculiar observations spark intense debate and research in the scientific community. One of the most discussed anomalies is the cold spot, an unusually large area of the CMB map that is significantly colder than its surroundings. This feature has prompted theories ranging from statistical flukes to the exotic, such as the influence of another universe in the multiverse model. Another intriguing anomaly is the alignment of the larger scales of the CMB temperature fluctuations with the ecliptic plane. This alignment is unexpected in the standard cosmological model and suggests that either there is a violation of the isotropy of the universe or a new factor at play that we do not yet understand. There is also the CMB's hemispherical asymmetry, where temperature fluctuations appear to be stronger in one half of the sky than the other. This asymmetry challenges the cosmological principle that expects the universe to be the same, on average, in all directions. The quadrupole and octupole moments of the CMB temperature anisotropies are observed to be lower than what theoretical models based on the inflationary cosmology predict. These moments are crucial for understanding the geometry and content of the universe, and their unexpected values prompt revisions in cosmological theories. Another aspect that baffles astronomers is the so-called axis of evil. This is an unusual pattern in the data, where the largest modes of CMB temperature anisotropy are seemingly correlated with the motion and orientation of the solar system, which defies the assumption that the CMB should be the same in all directions. The implications of these anomalies are profound. They might suggest that some aspects of the standard model of cosmology, such as the theory of inflation, need modification. Alternatively, they could point to new physics that has not yet been incorporated into the standard model. Despite extensive studies, these anomalies persist in the data from different CMB observations. This consistency across multiple missions adds to the intrigue, suggesting these features are not just instrumental errors or data processing artifacts. Some cosmologists consider these anomalies as clues to a more complex universe than the standard cosmological model describes. They might indicate interactions with other universes, hint at unknown forms of matter or energy, or suggest modifications to our understanding of gravity, or the early universe's expansion. Dealing with these mysteries requires not only more precise data, but also innovative theoretical approaches. New models and hypotheses are continuously being developed and tested, pushing the boundaries of physics and astronomy. Future missions dedicated to observing the CMB aim to resolve or further probe these anomalies. Enhanced measurement techniques and new technologies promise to either confirm these anomalies as significant or attribute them to statistical variances. The study of these anomalies also highlights the interconnectedness of cosmology with other fields of physics. Understanding them might necessitate advances in particle physics, quantum mechanics, and general relativity, showcasing the multidisciplinary nature of investigating the universe. Incorporating these anomalies into a coherent theory may lead to a new understanding of the universe that is as revolutionary as the shift from the Earth-centric models to heliocentric models in the early days of astronomy. As cosmologists delve deeper into these mysteries, the role of dark matter, dark energy, and potential other unknown cosmic components becomes increasingly significant. These constituents might play a crucial role in explaining the observed anomalies in the CMB. Overall, the mysteries and anomalies found in the cosmic microwave background studies provide a fertile ground for scientific inquiry. They challenge existing theories, inspire new research, and deepen our quest for a comprehensive understanding of the cosmos. The term axis of evil refers to an intriguing alignment of the larger scales of the cosmic microwave background, CMB, anisotropies, with the plane of the solar system. This unexpected alignment challenges the assumption that the universe should be isotropic and homogeneous as dictated by the cosmological principle, suggesting a potentially preferred direction in the cosmos. This anomaly was first noted in the data from the Wilkinson Microwave Anisotropy Probe, WMAP, and later confirmed by Planck satellite observations. The persistence of this feature across different CMB studies hints at a significant deviation from the standard model of cosmology, which could indicate new physics or a need to revise our understanding of the universe's large-scale structure. The axis of evil could be indicative of several theoretical possibilities. Some cosmologists speculate it might suggest the influence of other universes within a multiverse framework. Others consider it might be a result of an unknown physical process happening in the early universe, or even a fundamental flaw in our understanding of the laws of physics. Apart from the axis of evil, other notable anomalies in the CMB data include the cold spot, a large region of the CMB sky that is significantly colder than expected. This feature has generated discussions about its origins, whether it could be due to supervoid structures or is simply a statistical fluke. Another anomaly involves the scale-dependent damping tail in the CMB power spectrum, where the amplitude of fluctuations is suppressed more than what the standard cosmological model predicts. This suppression could imply physics beyond the standard model, possibly involving interactions between neutrinos and other dark sector particles. There's also the issue of hemispherical asymmetry, where one half of the CMB sky appears to have stronger temperature fluctuations than the other. This challenges the principle that the universe should look the same in every direction on large scales, and may suggest new dynamics in the inflationary period of the early universe. These anomalies are significant because they offer potential windows into the very fabric of the cosmos. They force theorists to question and revisit fundamental assumptions about the universe's uniformity, the nature of inflation, and the behavior of dark matter and dark energy. To understand these anomalies, Scientists employ advanced statistical techniques to determine if these features are indeed signals of new physics or merely artifacts of foreground contamination or data analysis methods. This rigorous scrutiny is essential to solidify our understanding of the CMB's implications. Future experiments and missions aimed at observing the CMB, such as the Simons Observatory and the proposed CMB-S4 project, are expected to provide even more precise data. These observations will help determine the statistical significance of these anomalies and either confirm their cosmological origin or attribute them to observational biases. The ongoing debate about these anomalies also highlights the need for interdisciplinary approaches in cosmology, integrating insights from particle physics, quantum field theory, and general relativity. This integration is crucial for developing a more complete theory that can account for all observed phenomena in the cosmos. By exploring these anomalies, scientists not only challenge existing paradigms, but also enhance computational methods and theoretical models. Each anomaly serves as a puzzle piece in the broader picture of cosmic evolution, offering clues that could lead to breakthroughs in understanding space, time, and matter. Addressing these CMB anomalies is not just about adjusting cosmological models, but also about the philosophical implications of discovering that the universe may not be as uniform as once thought. Such findings have profound implications for our place in the cosmos and the ultimate nature of reality. The discussion of the axis of evil and other CMB anomalies remains a vibrant field of study, reflecting the dynamic nature of scientific inquiry, where each answer leads to new questions. These discussions encourage a continuous re-evaluation of our cosmic theories and a deeper investigation into the unknown. As we probe these anomalies further, we may find that they represent the keys to unlocking new realms of physics, potentially leading to a new understanding of the universe that is as revolutionary as the initial discovery of the CMB itself. In summary, the exploration of these anomalies represents a crucial frontier in cosmology. It challenges scientists to think beyond the conventional, potentially leading to new discoveries about the universe's earliest moments, its fundamental forces, and its ultimate fate. Several current theories have been proposed to explain the anomalies observed in the cosmic microwave background, CMB, ranging from those tweaking existing cosmological models to those introducing entirely new physics. Each theory aims to account for these unexpected findings while preserving the successes of the standard cosmological framework. One theory suggests that the axis of evil and other large-scale anomalies may be due to the influence of a cosmic texture, a relic from phase transitions in the early universe. These textures could act as seeds for the anisotropies observed in the CMB, introducing non-uniformities that could explain the alignment with the ecliptic. Another hypothesis posits that the anomalies could be a result of topological defects in the fabric of spacetime, such as cosmic strings. These defects, predicted by some models of the early universe, could create disturbances in the CMB as they interact with inflationary perturbations. Some theorists propose that the hemispherical asymmetry and the cold spot could be evidence of a non-standard inflationary model. These models include variations where inflation occurred at different rates in different parts of the universe, leading to a more uneven cosmic expansion. Modified gravity theories have also been suggested as a potential explanation for some of the CMB anomalies. These theories alter Einstein's general relativity at cosmological scales and could lead to different patterns of fluctuation in the early universe. The possibility of a multiverse has been considered as an explanation for some of the observed anomalies. In this scenario, our observable universe might be one of many, each with different physical constants and properties. Collisions or interactions between these universes could leave detectable imprints in our CMB. Quantum entanglement on cosmic scales has been proposed as another explanation. This theory suggests that large-scale quantum phenomena in the early universe could lead to correlations in the CMB temperature field, which appear as anomalies. Some explanations focus on the role of dark flow, a hypothesized large-scale flow of galaxy clusters under the gravitational influence of structures beyond the observable universe. This flow could skew the distribution of matter and energy, affecting the CMB anisotropies. Another area of investigation is the role of dark energy, particularly its potential variations over time and space. If dark energy were not a constant, but varied throughout the history of the universe, it could lead to irregularities in the expansion rate, reflected in the CMB. A more controversial theory involves the idea of an anisotropic universe, where the laws of physics might vary subtly in different directions. This could arise from initial conditions in the early universe that were not perfectly uniform, leading to the observed anomalies. The impact of unseen astrophysical objects like supervoids or massive clusters is also considered. These massive structures exert a gravitational lensing effect on the CMB photons passing through or around them, potentially leading to anomalies such as the cold spot. Statistical flukes are also a grounded explanation, suggesting that while the universe is mostly uniform, random chance can lead to apparent patterns or features in the CMB that do not necessarily have deep cosmological significance. The integrated Sachs-Wolf effect, which involves the interaction of CMB photons with time-evolving gravitational fields, is another plausible mechanism. This effect can cause additional fluctuations in the CMB as photons pass through potential wells of varying depths. Simulations of the early universe, taking into account the detailed physics of the plasma and its interaction with radiation, suggest that some anomalies might arise naturally from complex dynamics that were not included in simpler models. As observational techniques improve and more data becomes available, the theories proposed to explain these anomalies will be tested with greater rigor. The ongoing dialogue between theory and observation is crucial for advancing our understanding of the universe and the fundamental laws that govern it. The future of cosmic microwave background, CMB, research is poised to be transformed by several ambitious next-generation experiments. These projects aim to enhance our understanding of the universe, tackling unresolved questions and testing the boundaries of our current cosmological models. One such initiative is the Simons Observatory, a ground-based project set to build on previous findings by providing more precise measurements of the CMB's temperature and polarization. The observatory will focus on refining the details of cosmic inflation and the properties of neutrinos, dark matter, and dark energy. The CMB S4 project represents another significant leap forward. This collaborative effort plans to deploy hundreds of thousands of detectors across multiple high-altitude sites. Its goal is to create the most detailed map of the CMB to date, examining even the faintest signals from the early universe to provide deeper insights into inflation and the particle content of the universe. The Lightbird satellite, a Japanese-led mission scheduled for launch in the 2020s, aims to measure the polarization of the CMB across the entire sky. Its focus is on detecting the B-mode polarization pattern, which is directly related to gravitational waves from the inflationary epoch, potentially providing a smoking gun signature of inflation. The Atacama Cosmology Telescope, ACT, continues to be upgraded with new capabilities to study the fine details of the CMB. These enhancements are designed to improve the measurement of the Sunyaev-Zeldovich effect, which provides information about galaxy clusters and the large-scale structure of the universe. The South Pole Telescope, SPT-3G, is another key player in this new wave of CMB studies. Equipped with a new camera that significantly increases its sensitivity, the telescope focuses on detailed observations of CMB polarization to better understand the dynamics of the early universe and the process of reionization. Each of these experiments is designed to leverage advancements in technology, such as enhanced detector sensitivity, broader frequency coverage, and improved polarization capabilities. These technical improvements are crucial for minimizing noise and separating the CMB signal from foreground emissions. The integration of data from these various next-generation experiments will also be vital. By combining observations from different instruments and vantage points, cosmologists hope to cross-verify findings and reduce uncertainties in the data. These experiments will also explore the small-scale anisotropies in the CMB more thoroughly. By studying these finer details, scientists can gain insights into the interactions between CMB photons and intervening matter in the universe, enhancing our understanding of cosmic structures and their evolution. Moreover, the next generation of CMB experiments will delve deeper into the mystery of dark energy. By mapping the distribution and evolution of cosmic structures over time, these studies will test theories about the nature and impact of dark energy on the universe's expansion. These projects also hold the potential to uncover new physics beyond the standard cosmological model, By pushing the observational limits, they may reveal anomalies or deviations in the CMB that could point to new particles, forces, or dimensions. Efforts to improve data analysis techniques will accompany these experimental advancements. Machine learning and advanced statistical methods will play crucial roles in processing the vast amounts of data expected from these experiments, helping to identify subtle patterns and correlations. The international collaboration is a hallmark of these next-generation CMB projects. Combining resources, expertise, and data from around the world, these collaborative efforts enhance the scope and depth of cosmological research. The educational impact of these projects is also significant. They serve not only as tools for scientific discovery, but also as platforms for training the next generation of scientists in astronomy, physics, and related fields. In conclusion, the future of CMB research through next-generation experiments promises to deepen our understanding of the universe's earliest moments, addressing fundamental questions about the cosmos and opening new frontiers in the field of cosmology. As we look to the future, a suite of upcoming missions and advanced technologies are set to significantly enhance cosmic microwave background, CMB research. These initiatives aim to deepen our understanding of the universe's early stages and the fundamental processes that have shaped its evolution. One of the most anticipated missions is the LightBird satellite, scheduled for launch by JAXA in collaboration with international partners. LightBird's objective is to detect the primordial B-mode polarization of the CMB. This polarization signature is linked to gravitational waves generated during cosmic inflation, offering potential insights into the universe's explosive growth moments after the Big Bang. Another pivotal project is the Simons Observatory, currently under construction in Chile's Atacama Desert. This observatory will combine the capabilities of several telescopes to probe the CMB with greater precision than ever before. Its advanced instrumentation aims to improve measurements of both the E-mode and B-mode polarization, providing clearer signals of the early universe's dynamics. The CMB-S4, Stage 4 ground-based CMB experiment, represents the next leap in observational cosmology. This extensive array of telescopes and super-sensitive detectors will be deployed at high-altitude sites across the world. CMB-S4 is designed to delve into the fine details of the CMB anisotropies and polarization, enhancing our understanding of dark energy and neutrino physics. The European Space Agency's ESA proposed core mission is another ambitious project that seeks to map the polarization of the CMB across a wide range of frequencies with unprecedented accuracy. CORE's comprehensive approach aims to address key questions in cosmology, from the mechanics of inflation to the properties of the fundamental particles. On the technological front, advancements in detector technology are revolutionizing CMB research. New developments in superconducting detectors, such as transition-edge sensors and kinetic inductance detectors, offer greater sensitivity and reduced noise, allowing for more precise measurements of the CMB's faint signals. Developments in multiplexing techniques are enabling these detectors to be read out en masse, significantly increasing the amount of data that can be collected and analyzed. This scalability is crucial for the next generation of large-scale CMB experiments, which will deploy tens of thousands of detectors. Digital signal processing is another area of technological advancement. Faster and more efficient data processing algorithms are crucial for handling the enormous datasets generated by modern CMB experiments. These advancements not only improve the speed of data analysis, but also enhance the ability to filter out noise and foreground signals. New software frameworks are also being developed to handle the complex data analysis needs of CMB research. These tools are designed to be flexible and robust, capable of processing the diverse data types collected by different instruments and experiments. Advancements in satellite technology and launch capabilities are reducing costs and expanding opportunities for space-based CMB observations. These missions are essential for minimizing atmospheric interference and obtaining a clear view of the CMB across the entire sky. Balloon-borne experiments, such as SPIDER and EBEX, continue to play a significant role in CMB research. These missions can carry instruments to the edge of space, providing a cost-effective method for collecting high-quality data with minimal atmospheric contamination. Interferometry techniques in CMB research are also advancing, providing new ways to measure the CMB's fine-scale structure. These techniques can help isolate the signal from the cosmic background, from other sources of microwave radiation, improving the clarity of the results. Collaborative international efforts are increasing, pooling resources and expertise across countries and continents. These collaborations are not only pooling financial and technological resources, but also fostering a global scientific community focused on unlocking the mysteries of the cosmos. Educational outreach and public engagement are also integral parts of these upcoming missions. By involving the community and educating the next generation, these projects aim to inspire a broader interest in cosmology and science as a whole. In conclusion, the future of CMB research is bright, with upcoming missions and emerging technologies poised to push the boundaries of our understanding of the universe. These efforts promise to unveil the secrets of the cosmos, providing deeper insights into its most fundamental forces and constituents. The next wave of cosmic microwave background, CMB research, is poised to deliver potential breakthroughs that could revolutionize our understanding of the universe. Each technological and theoretical advance brings us closer to answering fundamental cosmological questions. One of the most anticipated breakthroughs involves detecting the B-mode polarization patterns in the CMB. These patterns are signatures of gravitational waves generated during cosmic inflation, an explosive expansion that occurred fractions of a second after the Big Bang. Confirming these signals would provide definitive evidence for inflation and help determine its energy scale. Another significant potential breakthrough could come from improved measurements of the CMB's fine-scale anisotropies. These detailed observations might reveal more about the types of fluctuations that occurred in the early universe, offering insights into the nature of the quantum fields that drove inflation. The precise mapping of CMB polarization could also enhance our understanding of the ionization process, when the first stars and galaxies ionized the universe approximately 550 million years after the Big Bang. This could clarify the timeline of structure formation in the universe and the role of dark matter in the formation of cosmic structures. Advanced CMB studies might further our knowledge of the neutrino, potentially revealing the number of neutrino species and their masses. This information is crucial for understanding how neutrinos influence cosmic structures and the overall dynamics of the universe. Another potential area of breakthrough involves the mysterious dark energy. By studying its effects on the evolution of cosmic structures and the expansion rate of the universe, future CMB observations could provide clues about its nature and whether it has changed over time. Technological advances in telescope and detector design could lead to the discovery of new anomalies in the CMB data, challenging existing models and possibly indicating new physics beyond the standard cosmological model. Deeper investigations into the CMB could also refine our understanding of the Hubble tension, the discrepancy between different measurements of the universe's expansion rate. This could lead to a re-evaluation of the standard model of cosmology or introduce new concepts in astrophysical theory. A better understanding of cosmic inflation might also emerge from these studies. By observing the detailed properties of the CMB, scientists hope to learn more about the field that drove inflation and its potential connections to other fundamental forces and particles in physics. The integration of CMB data with observations from other cosmological probes, such as galaxy surveys and gravitational wave detectors, is expected to create a more comprehensive model of the universe. This synthesis could lead to breakthroughs in understanding how the large-scale structure of the universe has evolved. Studies of the CMB could even impact our understanding of fundamental physics, challenging and potentially confirming theories such as string theory or modifications to general relativity, which could be reflected in the structure of the CMB. Improved understanding of the initial conditions of the universe as revealed by the CMB might also help solve the mystery of the universe's ultimate fate. Whether it will continue to expand indefinitely, collapse, or reach a stable state could be determined by the properties of dark energy and matter. Emerging technologies might also allow us to probe the very edges of the observable universe through the CMB. This could open up new areas of study about the boundary conditions of the cosmos and what lies beyond the observable universe. The potential for discovering unknown particles or fields that interact with the CMB could also redefine our understanding of the particle zoo in particle physics, adding layers to the standard model or revising it substantially. In conclusion, the potential breakthroughs in CMB research hold the promise not only of deepening our understanding of cosmology, but also of linking it more closely to particle physics, astrophysics, and fundamental theories of forces and matter. These discoveries stand to chart a course for scientific inquiry well into the future, continuing to challenge and expand our view of the universe. The field of cosmology is constantly evolving, driven by both theoretical developments and new observational data, particularly from studies of the cosmic microwave background, CMB. These advancements are deepening our understanding of the universe's most fundamental aspects. One of the most significant theoretical developments in recent years has been the refinement of inflationary theory. This model proposes a period of rapid expansion shortly after the Big Bang, which helps explain the uniformity and flatness of the universe. Current research focuses on pinpointing the types of quantum fields responsible for inflation and their potential connections to other forces and particles in physics. Another key area of theoretical progress involves dark energy, a mysterious force that is accelerating the expansion of the universe. Theorists are exploring various models, including quintessence and the cosmological constant, to explain its properties and behavior over time. Dark matter, too, continues to be a crucial focus of theoretical development. While its gravitational effects are well documented, the particle nature of dark matter remains unknown. Theories range from weakly interacting massive particles, WIMPs, to more exotic possibilities like axions and sterile neutrinos. The integration of CMB data with other cosmological measurements is leading to the development of a more unified model of cosmology. This synthesis involves combining observations from galaxy surveys, supernovae, and gravitational waves to create a cohesive understanding of the universe's history and structure. Modifications to general relativity are also being theorized in an attempt to reconcile it with quantum mechanics and to better explain cosmological observations that do not fit neatly into Einstein's framework. These include theories like FR gravity and theories involving extra dimensions. The concept of the multiverse has gained traction as a theoretical framework that could explain many observed phenomena, including the values of fundamental physical constants and the fine-tuning of conditions necessary for life. This theory posits that our universe is just one of many, each with different physical laws or constants. Quantum cosmology is an emerging field that attempts to apply the principles of quantum mechanics to the entire universe. This includes studying the wave function of the universe to understand the conditions at the Big Bang and immediately afterwards. The potential detection of primordial gravitational waves through CMB polarization measurements is driving theoretical work on the early universe's energy scales. This could provide insights into unification theories that aim to merge all fundamental forces. The ongoing Hubble tension, a discrepancy in measurements of the universe's expansion rate, is prompting new theoretical models. These models explore whether new particles or alterations to the laws of gravity might explain this variance. Neutrino cosmology has also become a vital part of theoretical developments, as neutrinos affect the universe's rate of expansion and structure formation. Understanding their mass and number of types has significant implications for cosmology and particle physics. The study of cosmic reionization is leading to new theories about the first stars and galaxies. Theorizing how these early objects influence the universe's evolution involves complex models of star formation, galaxy evolution, and feedback processes. Another intriguing theoretical development is the study of cosmic voids, large, empty spaces in the universe. These voids can tell us about the nature of dark energy and the large-scale structure of the cosmos, challenging existing theories about the distribution of matter and energy. Theories involving cosmic entropy and the arrow of time are exploring how the universe's expansion impacts the flow of time and the evolution of complexity. These studies link thermodynamics with cosmological expansion, providing a broader context for understanding the universe's fate. In conclusion, the current theoretical developments in cosmology are rapidly transforming our understanding of the universe. Each new theory and refinement brings us closer to answering profound questions about the cosmos, from its earliest moments to its ultimate fate. Emerging theories and models in cosmology are pushing the boundaries of our understanding, proposing novel explanations for complex phenomena and addressing gaps in existing theories. These developments are reshaping our view of the cosmos and how it functions at the most fundamental level. One exciting area of theoretical development involves modifications to the standard model of particle physics to accommodate dark matter. Theories such as supersymmetry propose new particles that could account for dark matter, potentially observable through indirect detection methods like anomalies in cosmic rays or direct detection in underground experiments. Theories of dark energy are also evolving, with models like dynamic scalar fields, known as quintessence, which suggest that dark energy's strength might change over time, unlike the cosmological constant, which remains constant throughout the universe's history. Another frontier in theoretical cosmology is the exploration of extra dimensions beyond the familiar 3 spatial dimensions and 1 time dimension. Models derived from string theory propose that these additional dimensions could explain why gravity is weaker compared to other fundamental forces. The inflationary multiverse theory continues to gain attention, as it suggests our universe is just one of many bubbles in a larger multiverse. Each bubble could have different physical laws, driven by different rates of inflation, which could solve the fine-tuning problems in cosmology. Loop quantum gravity is emerging as a contender to string theory for explaining the quantum aspects of gravity. It posits a discrete structure of space-time, potentially eliminating singularities and providing a framework for the conditions at the Big Bang. The integration of information theory with cosmology is another innovative approach. This perspective views the universe in terms of information processing, with implications for understanding black hole thermodynamics and the holographic principle. The study of cosmic inflation is also being enhanced with new models that account for a range of inflationary scenarios, not just a single, rapid expansion. These models include features like multiple fields driving inflation or variations in the field potential, leading to different observational signatures in the CMB. Cosmologists are increasingly exploring the role of quantum effects in the early universe, particularly how quantum fluctuations might have influenced cosmic structures. This includes studying how these fluctuations translate into macroscopic phenomena via processes like quantum decoherence. There is growing interest in alternative theories of gravity that do not require dark matter to explain the dynamics of galaxies and galaxy clusters. These modified Newtonian dynamics, MOAND, and theories like TVS suggest modifications to gravity at low accelerations, which are typically observed at galactic scales. Simulations of structure formation are becoming more sophisticated, incorporating not just gravity, but also complex baryonic physics, including feedback from stars and active galactic nuclei, which influences galaxy formation and evolution. The concept of dark fluid combines dark matter and dark energy into a single framework, aiming to explain both the acceleration of the universe's expansion and the formation of structure in the universe through a unified theory. Neutrino cosmology is being enhanced by incorporating the mass of neutrinos, which impacts the rate of cosmic expansion and structure formation. This requires new theoretical developments and more precise measurements of the CMB and large-scale structure. Causal set theory is a lesser-known approach that models space-time as a discrete set of events ordered by causality. It provides a potential avenue for reconciling general relativity with quantum mechanics and understanding space-time at the Planck scale. As observational capabilities improve and more data becomes available, these emerging theories and models in cosmology are tested and refined, continually pushing the frontier of what we know about the universe. This ongoing process ensures that our cosmological models remain robust, comprehensive, and reflective of the actual workings of the cosmos. Despite significant advancements in our understanding of the cosmic microwave background, CMB, several challenges and questions remain that continue to puzzle cosmologists and drive further research in the field. One of the primary challenges involves the precise measurement of the CMB's polarization. Detecting the faint B-mode polarization, which could provide evidence of gravitational waves from cosmic inflation, has proven to be exceptionally difficult due to noise and contamination from foreground sources. The exact nature of the anomalies observed in the CMB, such as the cold spot and the axis of evil, continues to be a topic of debate. Determining whether these features are statistical flukes or signals of new physics requires more data and sophisticated analysis techniques. The integration of CMB data with other astronomical observations presents its own set of challenges. Discrepancies, such as the tension between CMB-based measurements of the Hubble constant and those made using supernovae and the cosmic distance ladder, need to be resolved to ensure a consistent cosmological model. Understanding the role of dark matter and dark energy in the early universe is another ongoing challenge. While their gravitational effects are evident in the CMB and large-scale structure, their exact properties and how they interact with ordinary matter and each other remain elusive. The implications of CMB studies for theories of gravity are profound. Modifying general relativity to account for observed phenomena, without invoking dark matter or dark energy, for example, requires a careful rethinking of the theoretical foundations of cosmology. The process of reionization and its timing is another area that is not fully understood. While the CMB provides some information about when the first stars and galaxies reionize the universe, details about how this process unfolded and its impact on cosmic evolution are still being studied. The mass of neutrinos and their effect on the early universe is a subtle aspect of CMB analysis that presents a significant challenge. Neutrinos affect the rate of expansion and structure formation, but pinning down their exact contribution requires extremely precise measurements. Quantifying the non-Gaussianities in the CMB is critical for understanding the physics of the inflationary epoch. These non-Gaussian features can provide insights into the interactions and dynamics of the inflationary field, but require high levels of precision to detect reliably. The search for primordial non-Gaussianity, which could indicate interactions in the early universe that deviate from the simplest inflationary models, remains a challenging frontier. These signatures are faint and require next-generation experiments to detect. The calibration and interpretation of data from different CMB experiments also pose challenges. Each experiment has its own systematic biases and uncertainties, and reconciling these across different data sets is crucial for building a coherent picture of the cosmos. Addressing the cosmic variance problem, the statistical uncertainty inherent in observing the universe from only one vantage point, is another challenge. This limits the accuracy with which cosmologists can measure large-scale properties of the universe. The development of new technologies and instruments for CMB research is a continual challenge. These tools must achieve unprecedented levels of sensitivity and precision while minimizing errors and biases that could distort the cosmological data. The theoretical implications of CMB studies on particle physics are vast. Linking cosmological observations with particle physics experiments, such as those conducted at particle accelerators, requires a nuanced understanding of both fields and poses a significant interdisciplinary challenge. Finally, the educational and philosophical implications of CMB research are immense. Communicating these complex concepts to the public and integrating them into our broader understanding of the universe requires careful thought and effective outreach. In conclusion, while the study of the CMB has already revolutionized our understanding of the cosmos, the remaining challenges and questions keep the field of cosmology vibrant and dynamic, continually pushing the boundaries of science and our place in the universe. The cosmic microwave background, CMB, has been pivotal in shaping our understanding of the cosmos. It serves as the afterglow of the Big Bang, providing a snapshot of the universe just 380,000 years after its inception, long before stars and galaxies formed. The significance of the CMB in cosmology cannot be overstated. It is the oldest light we can observe, carrying with it information from the early universe that has been crucial for developing the Big Bang theory, confirming that the universe originated from a hot, dense state. Through precise measurements of the CMB, cosmologists have been able to determine key cosmological parameters with remarkable accuracy. These include the universe's age, the rate of its expansion, and the composition of matter and energy that fills it. The CMB has also provided strong evidence for the inflationary model of the early universe. This theory, which posits a rapid expansion shortly after the Big Bang, explains the uniformity and flatness observed in the universe, and the CMB's subtle temperature fluctuations support this model. These fluctuations, or anisotropies, seen in the CMB are particularly significant. They are considered the seeds of all current structures in the universe. By mapping these minute temperature differences, cosmologists can trace the formation of large-scale structures like galaxies and clusters. The study of the CMB also intersects with fundamental physics, testing theories of gravity, and the nature of the early universe. It challenges and refines models of dark matter and dark energy, two of the most mysterious aspects of the cosmos. CMB research has led to a better understanding of the universe's composition, revealing that ordinary matter, which makes up stars and planets, constitutes only a small fraction of the cosmos, while dark matter and dark energy fill much of it. Another significant aspect of the CMB is its polarization, which provides insights into the universe at the time of recombination when photons decoupled from matter. This polarization offers clues about the conditions that prevailed in the early universe and the physics that drove its expansion. The CMB has also revealed the scale of homogeneity of the universe and confirmed that on large scales, the universe is isotropic, looking the same in all directions, a fundamental assumption of cosmology known as the cosmological principle. Technological advancements in observing the CMB have pushed the boundaries of astronomy and cosmology. Each new generation of telescopes and detectors has brought more detailed data, sharpening our image of the early universe and improving our understanding of cosmic phenomena. The anomalies and irregularities observed in the CMB, such as the cold spot and the axis of evil, continue to challenge standard cosmological theories, providing avenues for new research and theories that might explain these peculiarities. The educational impact of CMB research is also profound. It has become a cornerstone of modern cosmology, influencing curricula in physics and astronomy, and sparking public interest in the origins and fate of the universe. CMB studies have fostered international collaborations, bringing together scientists from around the globe to solve the mysteries of the cosmos. These partnerships have been crucial for pooling resources, sharing data, and developing new technologies. The ongoing study of the CMB not only deepens our understanding of the universe, but also continues to challenge our views on the fundamental forces and constituents of nature. It stands as a testament to human curiosity and the pursuit of knowledge. In summary, the cosmic microwave background is a cornerstone of cosmology, offering not just a glimpse into the early universe, but also providing a critical testbed for theories about the cosmos's structure, composition, and evolution. As we continue to study the CMB, we can expect it to yield more secrets about the universe, encouraging a deeper understanding of our place within it. As we conclude our exploration of the cosmic microwave background, CMB, and its profound impact on our understanding of the universe, it's clear that this field of study represents one of the most dynamic intersections of theory and observation in modern science. The journey through cosmology, from the theoretical predictions of the early 20th century to the groundbreaking discoveries and detailed mappings of the CMB, highlights the remarkable progress we have made in understanding the cosmos. It's a testament to human curiosity and the relentless pursuit of knowledge. Cosmology is not just about studying the large-scale structure and origins of the universe, it's also about understanding our place in the cosmos. The insights gained from the CMB tell us not only about the early moments of the universe, but also about the fundamental laws that govern all matter and energy. The study of the CMB has opened up more questions than answers, pushing the boundaries of physics, mathematics, and astronomy. Each anomaly and irregularity challenges our current understanding and invites us to think deeper, explore further, and consider possibilities we might never have imagined. For those intrigued by these mysteries, there's a wealth of knowledge waiting to be discovered. Whether you are a student considering a career in science, a teacher looking for materials to inspire the next generation, or a curious mind eager to understand more about the universe, cosmology offers endless opportunities. There are numerous resources available for those who wish to delve deeper into the study of the cosmos. From academic courses and textbooks to documentaries, public lectures, and open access research papers, the tools for learning are more accessible than ever. Participating in community science projects and astronomy clubs can also provide hands-on experience with observing the skies and contributing to real scientific research. These activities offer a practical understanding of the universe and foster a community of like-minded enthusiasts. Emerging technologies and future missions promise to unveil even more about the cosmos. Staying informed about these developments can be incredibly rewarding, offering a front-row seat to the latest discoveries as they unfold. Encouraging young people to explore cosmology and supporting their interest in science can have a profound impact. It is crucial for developing the next generation of scientists who will continue the work of unraveling the universe's mysteries. The discussions and debates that arise from studies of the CMB and cosmology are not just academic. They touch on philosophical questions about the nature of reality, the origins of the universe, and the ultimate fate of all things. As we look to the future, the potential for new theories and models to explain the unknown aspects of the universe remains open and vibrant. The field of cosmology is a reminder that science is always evolving, and there is always more to learn. Viewers who are captivated by the story of the CMB and the broader universe are encouraged to keep questioning, keep learning, and stay curious. Every observation and theoretical development enriches our understanding of the universe and our place within it. The exploration of cosmology is one of the greatest scientific adventures, one that connects us across nations and generations. It is a journey that combines the intellectual rigor of science with the existential and philosophical inquiry into our very existence. In closing, whether you are a seasoned astronomer or someone just starting to explore the night sky, the study of cosmology offers a unique perspective on the universe. It invites all of us to look up and ponder the cosmos, pushing us to think bigger and go further than we ever have before. Thank you for joining us on this fascinating journey through the cosmos. As we continue to explore and understand more about the universe, we invite each of you to be part of this exciting adventure, contributing your own observations, questions, and discoveries along the way. If you enjoyed this journey through the cosmos and are curious to learn more about the universe, don't forget to like, subscribe, and click the notification bell. Join us as we continue to explore the mysteries of the cosmos together. Your support helps us bring more fascinating content your way.